Hi, I'm Ben Toma, the mechanical lead for the assembly, test, and launch operations of the Mars Science Laboratory project. We've already sent the heat shield, the back shell, and the cruise stage. And on this trip, we're sending the descent stage and, of course, the Curiosity rover herself. There's an enormous amount of logistics involved in planning such an operation. When you're talking about moving an entire spacecraft, along with all of its support equipment, literally across the country, it takes months and months of planning and weeks to execute. Curiosity is flipped upside down for its ride to Kennedy Space Center in the same orientation that it'll be for launch. In this orientation, we carefully wrap Curiosity in a big, huge bag. That bag acts not only as a Faraday cage, but it keeps Curiosity clean for her journey to Florida. When she's all bagged up and ready, we have many engineers and many technicians gathered around and safely lift Curiosity up and down into her shipping container base. We'll lift a big lid on top of that shipping container. It's that shipping container that is then used to transport her across the roads and across the air on her journey to Florida. We actually arrive at Kennedy on a C-17, a military cargo plane, which will land at the same landing strip that the shuttle lands at. The team and I are really looking forward to our launch this November from Kennedy Space Center. I'm Ben Toma, and this has been your Building Curiosity update.
Hello everyone, my name is David Gruhl, and I'm the Assembly, Test, and Launch Operation Manager for the Mars Science Laboratory project. I'm coming to you from a clean room at the Kennedy Space Center, where my team is currently conducting the final functional test of the MSL flight hardware destined for Mars. I'd like to take a moment and introduce you to the flight vehicles that make up the MSL spacecraft, and then introduce you also to the Curiosity rover. Over here, we have our cruise stage. The cruise stage is comprised of a solar array, several guidance sensors, and a propellant system that basically gets the MSL spacecraft from Earth to Mars. Once we get to Mars, the vehicle will have served its purpose and we jettison it and it burns up in the atmosphere before we actually make first contact with the atmosphere itself. Over here, we have part of the aeroshell that protects the vehicle as we go through the Martian atmosphere. The back shell is the vehicle over here in white, which provides an interface to a large deceleration parachute. And over here is the heat shield, and the heat shield has the protective insulative tiles that keep Curiosity safe as all the heat is generated as we actually wake our way through the Martian atmosphere. Behind me is the descent stage. The descent stage is the jetpack that safely gets Curiosity down to the surface of Mars. Unlike Pathfinder and the twin rovers Spirit and Opportunity, which utilized airbags to make it down to the surface, Curiosity relies on the descent stage and its jetpack to actually make it down to the surface. Using retro rockets and a terminal descent radar system, this is what actually carries Curiosity safely down to the surface so that it can actually get its wheels onto the ground and perform its science. Coming up next, we'll show you what Curiosity actually looks like and the configuration it will appear once it actually safely makes it down to the surface of Mars in August of next year. So here's the star of the show, the Curiosity rover. Here Curiosity looks the same way that she'll look when she makes it to the surface of Mars and deploys all of her mechanisms. Sticking up off the top deck of the rover is a remote science mast, which contains all of our stereo imagery. You can also see the 6 wheels, which will actually propel Curiosity around the surface of Mars, as well as the robotic arm, which is sticking off the front of the vehicle, with the turret, which allows us to do science on rocks that are in the vicinity of the rover and return samples to science instruments that are contained on the body of the rover itself. All total, there's 9 science instruments, which will return all sorts of exciting science from the surface of Mars. Up next for us, we're ready to start stacking the vehicle, and from there we're looking forward to a great mission as Curiosity launches and lands on the surface of Mars next year.
Hi, I'm Ashwin Vasavada, the Deputy Project Scientist for the Mars Science Laboratory mission and its Curiosity rover. So a lot of people wonder why Curiosity doesn't have solar panels like the Mars exploration rovers, Spirit and Opportunity. The Mars exploration rovers often found themselves short on power as dust settled on their solar panels. This was especially a problem in the short days of winter. We need a good, strong, and reliable source of power to keep Curiosity going for over 2 years on Mars. Curiosity is 2 times bigger, 5 times heavier, and has 15 times the weight of scientific equipment relative to Spirit and Opportunity. Like those rovers, Curiosity surveys the landscape and examines rocks up close. Curiosity's scientific mission involves driving around its landing site, perhaps up to 15 or 20 miles, collecting samples of rocks and soils with a big jackhammer drill located on the end of a 6-foot robotic arm. Those samples are delivered to the rover and analyzed with some very sophisticated and power-hungry analytical laboratory instruments. And that's where the MMRTG comes in. The multi-mission radioisotope thermoelectric generator is a power source that we've used for years to power spacecraft that have gone to the outer planets, and even the Apollo missions used it on the moon. Behind me you can see a full-scale model of Curiosity, including the generator in the back. On this half-scale model of the generator, you can see what's inside. The generator contains a specially produced form of plutonium dioxide. The natural decay of this radioisotope gives off heat, which these thermocouples can turn into electricity. The generator provides both electrical power and heat to the rover. About 100 watts of electrical power is used to continuously charge the rover's battery. Also, heat can be pumped off of the generator using pipes to keep the rover's insides warm, including the scientific instruments. With Curiosity's generator, there's a guaranteed way of charging the battery year-round in all sorts of conditions. Curiosity's generator was developed by the Department of Energy and will be installed on the rover just a few days before launch. But to make sure everything works together properly, the engineers installed the actual generator on the rover for the first time. The blue light that you see was just additional lighting to help them make sure they could see what they were doing. The Curiosity rover and the spacecraft that'll take it to Mars are currently in Florida, undergoing its final preparations for launch. Everything's going well, and all of us on the science team can't wait for its launch later this year and its arrival to Mars next summer. I'm Ashwin Vasavada, and this has been your Building Curiosity Update.
I'm John Grotzinger, the project scientist for Mars Science Laboratory, the Curiosity rover, and we're going to take Curiosity to our chosen landing site in Gale Crater, which sits at the border between the southern highlands of Mars and the northern lowlands. A really exciting spot because it's very low, and that's the kind of place where water might have pooled and possibly formed lakes. So here we see a different view of Gale Crater that has a different perspective. You can see our landing ellipse down at the bottom there, which is the white circle, and in the middle of Gale Crater is this mountain of rock that is 5 kilometers high, made layer by layer by layer, but the layers at the bottom are the ones that we're most interested in because we think that those were deposited in an aqueous environment, which is very important for understanding habitability. What you can see here now is that we're about to land very close to the center of the landing ellipse, and we have a couple of different routes that we can take. The scientists on the team prefer the one on the right, and so what we would do is drive along it. And now you can see at the base of this mountain where these lower layers are, and the layers are important because they allow us to sort of read a geological book. You start at the bottom of the mountain, and those are the oldest layers, and then the layers that occur up near the top, those are the youngest parts, the youngest chapters in the book. We will drive along up to this outcrop that we call the fence, and when we get there, we're going to study it. It's a really attractive spot for us because it contains the kind of minerals that formed in water. And then when we're done with that, we're going to go beyond and we're going to enter a canyon. And this kind of terrain around here reminds us a lot of Sedona, Arizona. And all the rocks around here formed in aqueous environments. And so there's a lot of rock, hundreds of meters of it, layer after layer that we can study to tell us about the history of Mars at Gale Crater. Now we cross a boundary and we go into a very different type of rock. You can see how it weathers very differently. It's really rugged. So at that point in the mission, we'll be beyond our initial mission of 2 Earth years. This will take us into many years afterwards of exploration as we drive around this very rugged terrain. If we make it, we'll be able to look back over the area that we have previously studied, back down in towards the bottom of Gale Crater, back towards our landing ellipse.
Diving like a bird of prey, a NASA Dryden FA-18 has been putting the landing radar for the Mars Science Laboratory through its paces over Edwards Air Force Base in California. The aircraft carried an experimental pod that housed the test radar underneath the aircraft's left wing. During the flights, the FA-18 climbed to 40,000 feet, then made stair-step dives over Rogers Dry Lake at angles of 40 to 90 degrees
Holding it.
in order to simulate what the radar will see during entry into the Martian atmosphere. Being developed by NASA's Jet Propulsion Laboratory, the Mars Science Laboratory, with its Curiosity rover, is NASA's next exploration mission to the Red Planet.
After a virtual decades-long dead spell, the international space community is again turning its attention to our nearest neighbor, with lunar exploration projects in the plans of space programs the world over. But even before these are set to bear fruit, we'll be getting data back from even further afield, as mankind reaches towards the Red Planet and its satellites. Phobos Grunt is a much-hyped sample return mission to Mars's mysterious moon Phobos. It's a Russian-led project that will also transport a Chinese-made Mars orbiter when it lifts off this November. Aside from the long-standing attraction to the planet, Phobos piques scientists' interest thanks to theories it's actually an asteroid captured by Mars's gravity, a living laboratory of primordial space matter.
Because study the very early days of the solar system formation, study asteroids. We can't do it at the Earth because oceans, water, atmosphere, winds erase all this, wipes out all the memory from the first billion of years of the Earth's history. But studying asteroids, we could do this.
Updated since its first planned launch in 2009, Phobos Grunt is bigger and better. In addition to the transport and return vessels, as well as soil sampling equipment, the complex now carries the Chinese Martian orbiter, as well as an additional expendable fuel tank to propel the extra weight. Meticulous testing is underway at the Moscow Space Research Institute to assure the functionality of each Phobos Grunt component. The orbital trajectory of Mars and its moons reaches its closest point to Earth just once every 26 months. Catching Phobos at any other time is both more complicated and more costly. After missing the first launch window due to delays, scientists understand time is of the essence. The unfamiliar environment of the Martian moon's surface means every single piece of the more than 20 scientific instruments that make up the probe has high standards to meet and exceed.
Unlike lunar programs, here the task was undoubtedly complicated by the need to collect samples under tricky conditions. Gravity is virtually absent on Phobos.
While those aren't conditions easily recreated here on Earth, teams at the Space Research Institute have gone to great lengths to prepare the high-precision sampler that's at the heart of the Phobos mission. A computerized full-scale model of the robotic arm and sampling device was constructed for the purpose. As these samples could hold the secret to Phobos' origin, millimeter-scale precision is the key. The sampling device achieves that on just 5 watts of energy and under 200 grams of mass. In addition to testing the hardware assembly, the model has been helpful in honing the specially designed software that will guide the real Phobos Grunt soil sampler on the mission. This directs not only the probe itself, but the adjoined optical devices, including cameras and microscopes. Even the test soil was ordered from colleagues in geochemistry to be the closest possible simulation of the Mars moon's dirt. In all, there's every reason to be confident the apparatus will execute the mission's main objective. When Phobos Grunt arrives in orbit around Mars after a roughly 10-month journey, the Chinese orbiter will split off. After orbiting the Red Planet for around a year, the spacecraft will make its landing on the surface of Phobos. There it will take its samples and send them back to Earth for arrival in mid-2014. It's unprecedented research, a testament to the long-term, long-range capability of state space programs.
Eine Zenit-Trägerrakete ist erfolgreich vom kasachischen Weltraumbahnhof Baikonur gestartet. Die Sonde soll im kommenden Jahr den Marsmond Phobos erreichen und Daten zur Erde funken. Forscher erhoffen sich von der aufwendigen Mission Erkenntnisse über die Entstehung des Sonnensystems. 2014 soll eine Kapsel Bodenproben zur Erde bringen.
Nur wenige Stunden nach dem Start vom Weltraumbahnhof Baikonur ist der unbemannte Frachter vom Kurs abgekommen. Das hat die russische Raumfahrtbehörde Roskosmos bestätigt. Grund ist vermutlich ein defekter Motor oder eine fehlerhafte Software. Die Techniker haben jetzt nach Angaben von Roskosmos nur noch 3 Tage Zeit, um das Raumschiff wieder auf Kurs zu bringen.
Russia's mission is running into problems, I'm afraid. The unmanned probe was only launched yesterday. It's veered off course now, though. Scientists are hoping it can still be brought back on course over the next few days. Daniel Sanford has more.
It started as a textbook launch. The Phobos Grunt probe on top of a Zenit 2 rocket blasted off from Baikonur Cosmodrome in the middle of the night. Its destination, Phobos, the larger of Mars's 2 moons, though still just 16 miles long. But once the booster rockets had fallen away, the Russian spacecraft failed to fire its own engines to set it on its path to Mars, so it remains in orbit around the Earth. It seems its navigation system has failed. Engineers have 3 days to reprogram the craft's computer in a desperate attempt to salvage the mission before the batteries go flat. Phobos Grunt was designed to go into orbit around Mars and then land on Phobos in October next year to make observations of the main planet and collect soil samples before returning to Earth. It was always an ambitious mission, but no one expected it to fail so soon. Russia has had a successful half a century in space, launching the first man into orbit and even sending spacecraft as far as Venus and Halley's Comet. But somehow they've always been unlucky on their missions to Mars. Many have failed, and not one of them has been completely successful. Daniel Sanford, BBC News, Moscow.
Die russische Mars-Mission Phobos droht bereits kurz nach dem Start vom Weltraumbahnhof Baikonur zu scheitern. Die Weltraumsonde hatte sich gestern Abend planmäßig von der Trägerrakete gelöst, dann aber versagten die Triebwerke. Nun müssen die russischen Experten die Mars-Sonde in 3 Tagen wieder auf Kurs bringen, sonst ist die Mission gescheitert.
Rover der NASA ist startklar. Am 25. November soll Curiosity wie geplant auf Reise gehen. Er hat die Größe eines Geländewagens und soll im August 2012 auf dem Mars landen. 2 Jahre wird die Sonde dort nach organischen Materialien suchen. Die Forscher der NASA wollen herausfinden, ob es auf dem Mars jemals Leben gegeben hat.
Der neue supermoderne Mars-Rover Curiosity der NASA ist startklar. Am 25. November soll er auf die Reise zum roten Planeten geschickt werden. Curiosity ist etwa so groß wie ein Geländewagen und soll 2 Jahre lang auf dem Mars nach organischen Materialien suchen.
1, 0 and lift off.
That's it. That was a long day. 36 hours. About 3 hours of sleep in there somewhere. Half of it on a bus, half of it on a plane. But there it is. So now the journey really begins. As we led up to that whole operation, we had a huge set of work ahead of us. Stowing the rover and getting it ready for shipment meant a lot of shifts in a row, a lot of complex operations with the vehicle. And you have to remind yourself, every time you pick that rover up, it's almost $1 billion worth of hardware that you're watching out for every time you do something with it. So that part got to be really white knuckles for us. It makes us a little nervous sometimes. I mean, you worry about the environment. It's on a forklift. It gets put on the back of a flatbed truck and then run down the highway to March Air Force Base from JPL. And that whole transport is just like you're driving any other truck down the highway. So it's full of bumps and it takes lumps and so it's one of those that you worry about for sure. It's a very impressive operation to get the shipping containers up into the aircraft. These boxes are incredibly large, and even as big an aircraft as the C-17 is, it is barely big enough to fit these boxes. There's an entire team of Air Force reservists who help us load this, led by the load master, who was in charge of the winching operation. Basically, they use the aircraft cable system and hydraulic winch to hook up to the container and tow it on board. As that happens, you have a team of about 8 other Air Force crew members, plus all of the payload crew members, all of the MSL crew members that we had with us, watching all of the corners, making sure that everything was clearing and that the measurements were right, and that we weren't going to run into a problem if the shipping container got offline for any reason. Even despite the best planning, we can find ourselves in a spot where we still have to solve some of the problems. We need thick plywood to reduce the contact pressure on the wheels on the shipping container. You have this thing which weighs, 10,000 pounds or more, and you have to make sure you don't punch a hole in the aircraft floor. So we had to get thicker plywood. We had to make emergency calls out here to Kennedy Space Center to make sure that enough plywood was on hand when we landed, so that we would actually have that same accommodation on the way off of the aircraft.
May attention please, please remain seated with your seatbelt fastened until we reach cruise altitude. I will notify you when it is safe to move around. Thank you.
All of those operations had to be undone once we got down to the ground here at KSC, and so the operations on the tarmac, including the offloading of the shipping containers, had to be done just in the same way. The same crew then, after the 5-hour flight, stepped up and had to check all of those clearances again, make sure all of the rigging was out of the way, and that the winch system was ready to help lower the shipping containers down the ramp. You didn't want it to get the shipping container to get away from you and roll out onto the tarmac and get out of control. So, but they did a really nice, careful job. And again, we had all of the same crew that were there at March Air Force Base here at KSC, plus our arrival crew. We had a fresh crew of folks who are well rested to be able to take care of a lot of the ground operations once we arrived here, so that those of us who had been going for almost 48 hours straight didn't have to also finish out that part of the job. We're about to send our baby on a very long journey to go spend its life exploring the surface of Mars. It's a big leap of faith to be able to hand off the vehicle. They have a great team on the launch vehicle side, and they're ready to take care of her. But we are definitely nervous parents. We are wrapping up the last of the vehicle test and get ready to make it a real spacecraft here before too long. The mechanical engineers are working somewhere near that 12 to 13 hours a day at least to make it happen. We're at least going 6 days, if not 7 days a week for the next 3 or 4 weeks. It's going to be a big push, but that's kind of how the end game goes. We try to get things ready, and every last thing has to be done and done right. It takes a lot of time and a lot of effort to do it.
We have a lot of work to do in the next 2 months, because although the vehicle's in Florida and we've stacked it together just in the last couple of days, the rover's got its rocket jetpack on it, and the jetpack and the rover together have been put in the back shell of the vehicle, and right now we're putting the cruise stage on top. In some sense, that process is actually pretty straightforward. The challenge we have here in Pasadena is finishing up all our testing. All of our testing in our test bed and on the equipment, and going through and looking all the problems we had in our test program, make sure that all the problems we found were all solved, and that we know what we're going to do and how we're going to fly it. We're going through and doing last-minute fixes in the software, and there's quite a few little bugs that we need to get out of the system that we've discovered in our test program, and that's keeping us up.
3, 2, 1, fire.
Everyone stand by.
Rover deck.
Testing is a lot like renovating your house.
You can enumerate some very large, obvious things to do, and then when you do them, it becomes clear that there are some secondary things to do. And then when you do those, you discover third order, fourth order, ad infinitum. But at some point in renovating a house, you run out of money and have to stop. In the space business, you run out of time and you have to launch. We require our system to be able to be robust, to survive a number of different kinds of faults, both internal faults, things breaking on the spacecraft, or loss of sun data coming into the sun sensor, a variety of unfortunate circumstances we try to make our design robust to.
Not only have we driven the rover, we've removed its arm, put it all through its paces, but it's been in a thermal vacuum chamber and kept very cold. Parts of it have been on through in a centrifuge. We've done drop tests, pull tests, drive tests, load tests, stress tests. Just an amazing amount of testing this vehicle has gone through. We've done shorting tests. We've taken the vehicle and shorted electronics. We've looked to see that the radios all work together and that the rover doesn't interact with itself in bad ways. We've tried every way of operating the vehicle using the software, literally thousands and thousands of hours of software testing. It's been just an amazing several years, really, of constant testing and development, finding problems, fixing those problems, and going on to the next problem.
The system is sufficiently complex that anything you change has to be done with great care and caution, and then tested thoroughly because of the potential for side effects, unintended consequences of the fix. The first rule of engineering this late in the game is do no harm. Now that we're close to launch and really want to do no harm, kind of have to weigh the temptation to fix against the potential risk of messing something up and not having time to fix the thing we just messed up.
This is a very, very complicated beast. This is by far the most complex thing we've ever built. It's almost hard to imagine how complex it is. And in fact, if you get close up to the vehicle, you can see the richness of detail. And in fact, this vehicle almost has fractal-like complexity. The more you look at it, the more details that you uncover. And you have to make sure, when you're building this thing and testing it and designing it, that those interactions are well understood and that there is nothing about the system that will interfere with itself. And this has been a real challenge that we've had. And so every minute of the time we've had, we've been using that time with incredible intensity. And as a consequence, we're really getting tired. So hopefully we'll take a big breath in mid-November before we launch and be able to relax and let this vehicle off the ground and finally say goodbye. I think this rover's been on Earth for a little bit too long. I think she's ready to go.
NASA's newest Mars rover, Curiosity, began its launch site preparation in Florida on May 12, 2011. That's when the first 3 elements of the spacecraft, officially known as the Mars Science Laboratory, were delivered to Kennedy Space Center Shuttle Landing Facility aboard an Air Force C-17 cargo plane. After the cruise stage, back shell, and heat shield were unloaded and transported to the Payload Hazardous Servicing Facility, processing got underway. Technicians installed a solar array panel to the cruise stage and processed the spacecraft's back shell. The back shell carries the parachute and several components used during later stages of entry, descent, and landing of the rover. The aeroshell, comprising the back shell and the heat shield, was tested on a spin table before technicians used an overhead crane to separate the 2 components. On June 22nd, a cargo plane arrived at Kennedy carrying the rover and the spacecraft's rocket-powered descent stage. The descent stage will fly the rover during the final moments before its landing on the Martian surface. After transportation to the servicing facility, technicians removed the protective wrapping from the descent stage thrusters for documenting and inspection. The rover itself was removed from its protective carrier and moved by crane to a work stand. The rover's processing and testing began, including a series of rotation tests. The wheels, as well as the instrument mast and science boom, were put through a series of deployment tests. Enclosed in a shipping cask, the spacecraft's power-generating multi-mission radioisotope thermoelectric generator arrived at Kennedy June 30th and was moved to a storage facility where workers removed the cask. A fit check of the generator was conducted in July. Also in July, the rover's launch vehicle began to take shape. A United Launch Alliance Atlas V with 4 solid rocket boosters attached will loft the Mars Science Laboratory into space. The Atlas V first stage and Centaur second stage were offloaded from the Delta Mariner transport ship at Port Canaveral, just a few miles from the launch site. They were transported to Cape Canaveral Air Force Station and delivered to the Atlas Spaceflight Operations Center. A crane was used to position the 106.5-foot-long stage inside the integration facility and lower it onto its launch platform. Several days later, technicians began the installation of the 4 solid rocket motors, using a lifting device to elevate them to an upright position. An overhead crane lifted the Centaur upper stage of the rocket, and technicians attached it to the lower stage. In the payload processing facility, the dual sections of the Atlas V payload fairing that will protect the spacecraft during launch and ascent were prepared. Technicians helped guide the rocket-powered descent stage over Curiosity for integration. Then they positioned the back shell as it was lowered over the rover for encapsulation. Technicians cleaned the fairing acoustic protection system to meet NASA's planetary protection requirements. The spacecraft's cruise stage was joined to the aeroshell containing Curiosity. The cruise stage provides solar power, thrusters for navigation, and heat exchangers to the rover during its flight from Earth to Mars. The spacecraft was then enclosed between the 2 halves of the payload fairing and placed on a transporter for the move to Space Launch Complex 41. As dawn broke on November 3rd, the payload was ready to be lifted at Space Launch Complex 41's vertical integration facility. Once atop the rocket, the payload was attached and the radioisotope thermoelectric generator was installed. With its final Earthbound journey completed, the rover Curiosity and its Atlas V launch vehicle were ready for launch. Next stop, Mars.
The hope is that we land there and we can basically unlock the secrets of an environment that existed a few billion years ago on Mars that was potentially a place that life could have survived.
Mars has beckoned to Earthbound observers for centuries, seeming to appeal to astronomers to find out the secrets of the lone bright red dot among all the bright white stars in the nighttime sky. Those answers came sparingly, but as technology advanced on Earth, astronomers were provided new tools to get better and better looks at the planet closest to Earth in terms of distance and makeup. NASA put a wheeled robot on Mars for the first time in July 1997. About the size of a skateboard and weighing 23 pounds, the Sojourner showed Earth unprecedented views of the red planet as it rolled over the surface for 3 months, all within 500 meters of its base station. Now, NASA is on the verge of launching another rover to Earth's nearest planetary neighbor, one that is nearly 1,000 times heavier than Sojourner, and packing a mobile laboratory designed to look closely at what the planet is made of. The rover is called the Mars Science Laboratory, or MSL. It's also known as Curiosity, and its results may answer one of the great questions of modern science.
Mars and Earth were made at about the same time, and yet they've had very different evolutionary pathways. We seem to be verdant and full of life, and Mars is quite cryptic. So we'd like to understand a little bit about the past of Mars. In fact, we'd specifically like to know whether or not Mars has ever been habitable, perhaps in some distant time, perhaps now beneath the surface.
When it comes to Mars, history has shown mission planners they cannot take any aspect of the launch, flight, or landing for granted. NASA, the Russians and Soviets, and the European Space Agency all lost missions to the red planet at one time or other.
It is tough to land on Mars. Sometimes it's even tough to orbit Mars. So Mars is difficult. Anytime you're going that far out and you're making that transition from not only orbiting and taking pictures, but add the complexity of slowing yourself down, putting a target on that planet and landing there. That's awesome.
Launches to Mars also come with a strict time limit when the planets are aligned correctly to allow a flight.
For MSL, we only get an opportunity every 24 to 26 months. If you miss it, you have to wait.
Curiosity is to begin its flight to Mars packed inside the nose cone of an Atlas V rocket. It will fly through space for 9 months before beginning its work on the surface in August 2012. Like every mission to Mars, this one carries the most advanced tools available to conduct experiments on its own, millions of miles from Earth.
And then the real new thing for this rover is the ability to actually drill into rocks on Mars, collect powder from those rocks, and deliver that powder to two relatively large analytical chemistry laboratories that are located inside the rover itself. So we deliver that powder, and we can uniquely determine its mineralogy, what minerals are present, as well as what chemical elements are present. And this will really give the scientists the core information they need to figure out whether Mars was a habitable environment.
The rover is essentially like a geologist in a self-contained laboratory, and the capabilities that exist are probably the next best thing to sending a human astronaut to do the same job.
It will also beam back remarkable views from the surface using state-of-the-art cameras, including 3D lenses.
This is a vehicle on Mars, cruising around, drilling into rocks, chipping away at stuff to see what that planet's made out of. And even if it didn't do that, if it just cruised around Mars and took pictures, the value in that is tremendous.
Curiosity is not headed to just anywhere on the red planet. Scientists spent years searching for the best place to land the rover, somewhere that had the best chance to show the true past and present of Mars. That place is called Gale Crater. A 3-mile-high mountain stands in the center of the crater, and Curiosity will explore the sediments that have built up there and hopes that the soil will complete parts of the Martian puzzle.
And what's special about Gale is it has the thickest package of sediment that we've been able to identify on Mars. So it represents a lot of time, and hopefully we'll get some idea about what has happened over time.
If Mars was ever home to vast lakes and flowing rivers, which data from other spacecraft suggest, then the rocks and minerals at Gale Crater could reveal unimagined secrets about our closest planetary neighbor.
They suggest, in a tantalizing way, that perhaps they could have been deposited underwater. And of course, we associate water often with the possibility, the potential for habitability.
It's an ambitious mission, and the robot designed to pull it off is unlike any planetary rover devised so far.
My first thought, and I won't lie, was, wow. It's a very impressive spacecraft. The rover itself is much larger than anything that we've sent up before, but it's a very, very, very impressive spacecraft, and we're looking forward to some great science coming out of the mission.
We couldn't use airbags this time because of the weight of Curiosity. So we went back to using rockets, but the novel design is this little rocket jetpack that flies the rover down and then lowers the rover down on a tether, lands it on the ground, and then that rocket jetpack flies off and we're done with it. That leaves the rover ready to rove around on its wheels and explore Mars.
Relying on solar cells was ruled insufficient for a mission as ambitious as the Mars Science Laboratory. Simply put, they did not provide enough electricity for a year-round mission, nor would they produce enough power for the 10 instruments on the rover, some of which have to operate at the same time to fulfill their research goals. The rover may cover 12 miles or more during its 23-month mission, a goal that requires a steady amount of power. So the Department of Energy built for NASA a nuclear-powered electrical system instead, called a Multi-Mission Radioisotope Thermoelectric Generator, or MMRTG. It has no moving parts, but converts heat from a small core of plutonium into about 110 watts of electricity around the clock and all year. It's the same power source that enables probes to work in deep space on missions such as Galileo's examination of Jupiter, Cassini's unprecedented look at Saturn, and the New Horizons mission to Pluto on the farthest boundary of the solar system. It was also used on the surface of Mars by the Viking landers in 1976. NASA also takes extra precautions because of the power supply, including working with other federal agencies to ensure its safety on Earth and during launch. Looking at Mars through a telescope over the decades, astronomers have wondered what secrets the planet conceals. Even looking at the surface doesn't tell the whole story, which is why scientists have been eager to dig deeper every time they get a chance.
Those folks that actually had a hands-on role in building this thing, there's some separation anxiety, I bet you. But now the next phase is, hey, I get to drive this thing, or I get to use the hammer drill on something. So that aspect of it is great.
I've been working on Mars Science Laboratory for 7 years, and I'm extremely excited that we're getting ready to launch.
20 years from now, I think they'll look back and consider this a true landmark mission, a great stepping stone for human exploration beyond Earth orbit, and it will certainly be one for the history books.
Good afternoon, everyone. This is our briefing to help us answer the question, what do we know about Mars? And here to help answer that question is Michael Meyer, the lead scientist for the Mars Exploration Program, Bethany Ellman, scientist from the Jet Propulsion Laboratory, assistant professor at the California Institute of Technology, and John Grotzinger, the project scientist for the Mars Laboratory at the California Institute of Technology. And we'll begin first with Michael Meyer. Michael?
Well, thank you, George. For millennia, humans have been wondering about the red planet and studying it, and it's only recently that we've actually been able to go there and look. In 1976, we sent 2 missions there, the Viking missions. Both were orbiter and lander, and we sent them to the red planet. If I could have the first slide, please. So Viking landed, and this is from Viking 2, and it shows a cold, barren, dry, apparently dead planet. And as you might imagine, the enthusiasm for Mars exploration kind of took a plummet. But interestingly enough, during the same period of time, we found in the subsurface ocean life in scalding hot hydrothermal vents. And that started a whole line of study of looking at life in extreme environments. And through that study, we came to learn that life is capable of adapting to all sorts of environments where it seemed like the only real necessary ingredient would be liquid water. This was encouraging to the broad scientific community in understanding that there may be more places where life is possible than we originally thought. So we began the era of modern era of Mars exploration. So in 2 decades later, 1996, we sent the Mars Global Surveyor. Could I show the next slide? And what this slide shows is the missions that we've had sent to Mars since Mars Global Surveyor. And with that, we've had orbiters and landers. And with each successive mission, we've been able to increase the spectral and spatial resolution of our look at the red planet. And we've learned so much more. We've learned that Mars is a dynamic planet. We've learned that it has a history where it was warm and wet at the same time that life started here on Earth. And we know that it's gone through a massive transition from that more benign planet of early on to what it is today. And so we're actually here to give you a rundown on some of the things that we've learned in the last 10, 15 years about the red planet that encourage us to think that Mars is worth exploring for many different reasons, including the potential of having been habitable at least in its past. George?
Thank you, Michael. And now to Bethany Ellman, the scientist from the Jet Propulsion Laboratory and assistant professor from the California Institute of Technology. Bethany.
So I have the privilege of talking to you about some of the discoveries from this flotilla of missions that we've sent to Mars over the past decade. And if we can start with the first graphic, I'm going to begin the story with what we know about Mars as it is today. So these are the top highlights of what we know about Mars today. And so Mars today on this graphic is what you see in the top left of this picture. Mars, like Earth, is tilted on its axis and as it's spinning like a top. So Mars has seasons. You can see the two polar ice caps at the north and south of Mars. But Mars, unlike Earth, is not stable around its spinning axis. So what happens is that Mars's axis tilts. Okay, and what we found through a combination of modeling and observations of the surface is that this results in ice ages on modern-day Mars. You can see that when Mars is tilted more extremely than it is today, ice builds up around the equator. When Mars sort of straightens out along its axis, the poles grow in size. So this changing distribution of ice is one of the emerging stories that's come out of the work of the recent decades. And if we go to the next slide, we see evidence of this. The high-rise camera on the Mars Reconnaissance Orbiter is able to examine the surface at very high resolution. And what we've found is that impact craters that impact into the mid-latitudes of Mars have excavated ice from beneath the surface. And that's what you see in this image here, ice associated with these small craters. Now, this ice isn't stable at the surface. It's a relict of these past tilts and changes in Mars's obliquity. And so if we look back at this on the order of a few weeks and a few months at the same spot, the ice is gone, but it's a hint at past climate change. If we head to the next graphic, the other hint of this changing dynamic modern Mars is in this recent discovery where you can see from right to left these dark streaks emanating from the walls of a crater. These streaks were recently, in a recent paper by Alfred McEwen et al., the best hypothesis we have to explain those streaks is that they're formed by short-term discharge of briny waters when modern-day Mars heats up during the summer. For a brief period in time, this ephemeral, quick period of time, we may in fact have salty waters on Mars. So if we go to the next graphic, I've talked to you about modern Mars, a story of ice, very, very, very short-term rare water. But if we look at ancient Mars, this is a topographic map where red is high elevations, blue is low elevations. We're looking at the Mars globe, and I've oriented it so that you can see Mars has these enormous outflow channels and valleys that flow out, where water previously flowed out into the northern lowlands. That's that blue low depression toward the left-hand side of the screen. So liquid water was not short-term in the past. We know that it had a role in carving out these large channels. And if we head to the next graphic, it also had a role in depositing sediments within craters. Now this is an image that's a combination of some of the data sets from the Mars Reconnaissance Orbiter, the high-resolution camera, the context imager, and then overlaying are colors from the CRISM infrared spectrometer. And these colors, along with the spectra from pixels in this image, allow us to get at the composition of these sedimentary materials that were carried by the water. And now the key color here is the green, because the green materials have been identified as clays and carbonates. Now these are minerals that form in the presence of liquid water, and the clays in particular indicate the long-term presence of water interacting with the rocks, causing alteration of minerals. Clay minerals also have water in their structure. And if we go to the next graphic, we see these clay minerals and other hydrated minerals, so minerals with water in the structure, in different geological settings throughout the planet. This is just another example that we're able to get at now with this high spatial and spectral resolution of Mars, where we can pick out in the walls of this crater, kind of like the pages in a book, two different pages in Mars history, where early in Mars history we had an alteration, that process that formed iron magnesium clays, maybe not so much water flushing through, possibly in the subsurface. But on the top we have this unit with a higher degree of leaching forming aluminum clay. So two distinct periods in Mars history recorded in these strata. If we go to the next, I'm just going to provide another example, because here we go from clay minerals. Clay minerals form from long-term chemical interaction of water with rock, and they're the green color. Now the pink color are sulfate minerals, again, salt minerals identified through spectroscopy. Now, so this is just a subset, a small snapshot from a crater that's over 100 miles in diameter. And what we see when we look around that crater is this bathtub ring of salts. So in this crater, it was once filled with water, and upon evaporation deposited these sulfates sort of ringing around afterwards. What does this all mean? So if you go to the next graphic, what we think this means is that we can trace a progression in Mars history through both minerals and by careful examination of rock strata in a few key locations across the planet. Now on the bottom are Noachian, Hesperian, Amazonian. Their names you'll hear over the course of other press briefings, which are the traditional divisions in Mars time. What we think we see as we move from the Noachian is this clay era where there was abundant water chemically interacting with rocks. We move that and then into a drying period where you get sulfate salts deposited as the water begins to go away at the surface. And then you're in cold, modern Mars, where ice is the story, not liquid water. So there's this fundamental transition between the Noachian and the Amazonian, between the era of clays to the era of sulfates to the era of anhydrous minerals, where water doesn't appear to play a role. And it's that critical period that's spanned by the sediments at Gale Crater. We want to understand those transitions, so that's why we're headed there.
Thank you very much. And our next briefer is John Grotzinger, the project scientist for Mars Science Laboratory from the California Institute of Technology. John.
Great. Thanks, George. So what I'd like to do is take you back again to a few decades ago, and if we can have the first graphic. One of the motivating reasons for the Viking mission to land and look for evidence of life on the surface of Mars was a discovery of the channel network systems that you see here. These have been studied for decades now. I think it's safe to say that virtually the vast majority of the science community believes that these channels were cut by flowing water, emerging from the surface, subsurface, maybe flowing across the surface. But it's these channel systems that originally attracted so much attention for Mars. Now, in the more recent decade, there have been some spectacular discoveries that sort of fill out the rest of the story, because if you look at these channels, it's natural to ask, if water was flowing, where would it take all the materials that were eroded away to create the canyons? So if you go to the next display item, what we see here is a delta called Eberswald Delta. It was one of the potential landing sites for the mission. And it's at the end of one of these channel networks. And so we see all the material that got eroded by water here being deposited in water as a delta that almost everybody can recognize. And this is really amazing because in addition to this, there was also the discovery of clay minerals here. So we're beginning to see a more balanced picture of Mars, one where you have source areas that represent the interaction of water with rock to produce sedimentary materials that contain alteration products like clays, and then they get transported down river systems to form things like deltas that would have accumulated in bodies of standing water. And this is very attractive from a habitability point of view. And it creates the basis then for Mars Science Laboratory to have had a very exciting landing site selection process. So if we go to the next one, now we're going to jump up here more recently within the last 7 years, the discoveries by the rover Opportunity in the Mars Exploration Rover mission. And here we see a number of very important aspects that take us into our understanding of modern Mars. One is that we see layered rock, sedimentary rock, and the sedimentary rock on Mars we view in an analogous way to sedimentary rocks on Earth, which are the principal repository for all the records of life on Earth. And while Mars Science Laboratory is not a life detection mission, we are on a mission to investigate the building blocks of life, important chemical elements, and also potentially look for organic compounds. And when you have what a geologist calls a model like this, where you can look at the rocks and see that you had ancient sand dunes, environments where there was ancient groundwater, and then environments where you had ancient streams, this gives you a whole diversity of potentially different habitats. And this is just one example on Mars. You can go back to the locations that Bethany was talking about, the very ancient Mars, and you see a different type of geological history and a very different type of potentially habitable environments. So we're just on the cusp of beginning to come up with a whole range of these possibilities for us to explore into the future. Okay, so in the next one, now we take us into, as Bethany mentioned, there were the 3 eras where you went from dominantly clays, time when weathering, alteration of water produced clays, to a time when alteration of water produced a lot of sulfate minerals, to a time when apparently there were not many hydrated minerals that were formed, yet we still see the accumulation of sedimentary materials. And you might ask, what do you learn about Mars in the absence of water or in the absence of a potentially habitable environment for life if it had evolved on Mars? And this is a beautiful example of that. You see these very well organized strata. This is like a heartbeat, except this is the heartbeat of the planet's climate cycle. So just like on Earth we're very interested in climate change, on Mars we see this very rhythmic alternation of layers that creates a really spectacular record of past climate change on Mars. And then that takes us to the era that Bethany talked about first, where Mars is dominated more by ice and a very cold climate and atmospheric processes and transport of sediments by wind rather than water. So we can see in the rock record these different histories. Okay, so now if we go to the next one, what we see here is our destination for Mars Science Laboratory. This is Gale Crater. You'll hear a lot about it tomorrow at the press briefing tomorrow. There is a crater about 150 kilometers in diameter. That's about as big as the Los Angeles Basin, surrounded by the mountains that ring the Los Angeles Basin. And right there in the middle of it is a mountain about 5 kilometers high. That's as high as Mount Whitney, which is the tallest mountain in the lower 48 states. And if you go from the yellow dot, which is in the center of our landing ellipse, we have the ability to traverse in our mission through the first few hundred meters of strata that you see there. And then eventually, over an extended mission, it might be possible to go to the top of that mound. But the important thing I wanted to say about the mound today, to sort of lock in some of the points that we've been talking about, at the base of the mound, you see strata that are composed of clays and sulfates. As you go farther up the mound, you see strata that are composed of dominantly sulfates. And then as you get above the first 500 meters or so, you then go into strata that don't have hydrated minerals. They seem to be composed of these rhythmites from the drier time of Mars. So in one location, we can drive the rover through all these successive different environments and sample these various periods in the history of Mars that we've talked about. So I'll turn it back to George.
All right, thanks very much. We're ready now to take questions. So please give your name and affiliation when the microphone comes to you, and we'll start right here in the front with Ken.
Hi, Ken Kramer for Spaceflight Magazine. For Bethany and anyone else who wants to answer, please, a couple of questions. Can you describe the clays, how widespread they are on Mars, and the sulfates? Are they very narrow, or are they pretty widespread?
Right. So I should say that clays and sulfates were something that weren't even discovered until 2004 with the Mars Express mission from Europe. So they'd eluded detection so far, and that's because the exposures where we're able to see them are very small. And it makes sense if you think about the fact that they're ancient, and because they're ancient, they're buried by later materials. So with this high spatial resolution, we're able to see them. And where do we see them? So clays, to the extent that we are able to figure it out, they seem to be globally widespread, but frequently buried. And the way they're exposed often is in impact craters, where, again, we punch through the surface and these clays are thrown out for us to be able to see them. We also have a few places where tectonic activity has exposed a nice, thick stratigraphic section with the clays. But the clays do appear to be global. The sulfates also are regionally global, if that makes sense. There are a few regions scattered throughout the planet where we see sulfates. It appears that some work on hydrologic modeling groundwater flow through Mars, and orbital detections of sulfates are starting to converge, where it looks like where we see the sulfates are these zones where it's predicted that groundwaters would be upwelling and reaching the surface.
Okay. And for John, could you tell me, I think you said these channels you believe most are formed by water. So do you say that about Valles Marineris? It's mostly water? You don't think it's carbon dioxide? And also, how long is that distance from the yellow dot to the red dot? How quickly could you drive the rover?
Right. A couple of questions there. I think that, for a long time, as long as people have seen the channels, there's been a discussion about what the liquid was that carved them out. And as I said, I think that this is now stabilized on water as being the most likely material, and that's been bolstered recently by the discovery of hydrated minerals that do occur as transport weathering products in these channels. It was a prediction of that model. It was observed independently, and I think it shores the whole thing up. The second question about Valles Marineris is a different feature. It's not produced by erosion. It's dominantly produced by tectonic processes that involve big crustal motions that drop blocks down. And at the base of Valles Marineris, you do get thick successions of sulfates. One of the attractions of Gale to us is that without being able to fly into Valles Marineris, we capture a lot of the interest that you would get in going to Valles Marineris, because the bottom layers in Gale Crater are composed dominantly of sulfates, and they sit in a very low topographic depression, lower than the floor of Valles Marineris. So it's not the same as Valles Marineris, but it's maybe as close as you can get. And then the last question about the distance, our landing ellipse is about 20 kilometers in diameter, so we would drive outside of the landing ellipse on the order of about 12 kilometers to get to the first well-developed sulfate deposits and clays.
Okay, we have a question here in the back. Did you have a question?
Yes. Chris Haber, United Television Network. I was wondering, with the recent discovery of the shifting the sand dunes, are you planning on using Curiosity, if there's anything on board that you might be able to investigate further with the existing equipment that's already built into the rover?
Yeah. That would be a good question to bring up again tomorrow, because we'll have the principal investigator of the camera here, and that's one of his real interests. And so we have the ability to measure the wind speed on Curiosity, what direction the wind is blowing in, and then make measurements of the surface topography of the dunes and see if sand is being transported. We should be able to do that.
Marcia?
Marcia Dunn, Associated Press, probably for Dr. Meyer, but I'm not sure. Of the previous Mars missions, the several dozen that there have been, how many besides this one have actually looked directly or indirectly at the life issue? And what have you learned so far that this will build upon?
Well, I actually like to call Curiosity the first astrobiology mission since Viking. And basically that's because we're sending a gas chromatograph mass spectrometer which can look for organics and characterize them. And essentially it's similar, much better, but similar to the instrument that was sent on Viking. Here the huge advantage is that you can rove to wherever you think is the best thing to measure.
So there's been this gap then essentially in your mind?
Phoenix had a gas chromatograph mass spec on it that could have measured organics if there was sufficient amount, but it couldn't move around and is also on the northern polar layer terrain. So in many ways its goal was pointed more toward understanding the formation of the layer terrain and what the polar areas are like. So Curiosity, I think, is really the first one since Viking to approach the life question. Now, I should be clear that it doesn't have a life detection instrument on it in the sense that a camera is not a life detection instrument unless something hops in front of it. So the capability of SAM, the Sample Analysis at Mars, which is the gas chromatograph mass spec, is that it can look at organics and characterize them and make you more interested in Mars and what secrets it might hold. But unless you're extremely lucky, it's not going to tell you whether or not you found evidence of life.
Can I ask another question? What is it about Mars that makes it so treacherous getting there? So many missions have failed, including one in Earth orbit right now. What is it about Mars that makes it so tricky, so difficult to get to?
Well, one theory is gremlins. The other is just I'm not sure why we've been that unlucky, and it may be that early on in planetary exploration, Mars was a target such that as our spacefaring agencies were coming up to speed to how to do planetary missions, their first target was Mars. So there's a lot of failures early on and just with how do rockets work, how do you get there. So I think there was a big learning curve, and now we're just running into Mars is difficult, and so many things have to go right for a mission to work. But we have a much better track record than we did in the 70s.
Dan?
Dan Billow from WESH-TV. On the time-lapse photo you had that looked so much like surface water, give me a ballpark estimate, if you can, on how long that might persist, hours or days, and if you have any idea. And would you discuss a little bit more about to what extent the planet has kind of a subsurface layer of ice? Do you think that that's the case?
Yeah, I'll take that. So water, liquid water, is not stable on the surface of Mars today. So as for how long it sticks around, well, it's how long it takes for it to evaporate. So we're probably talking on the order of a few minutes. But what happens when that water is at the surface, it causes all these noticeable geological changes that we can then track. But we're talking really short periods of time.
But those features form and lengthen over a Mars. It starts, kind of in the spring, goes through the summer, and then they disappear in the fall. And it's happened on successive seasons. So although liquid water at the surface may be very short time, the moisture that's causing those features to form lasts over a whole season.
And a subsurface layer of ice or water, what are your thoughts on that?
Yeah, the thought is that it's a subsurface layer of ice is probably the most likely source for this water. And one of the things that may be causing it to melt periodically is the presence of salts, which just like you throw salt on the road in the winter to get the snow to melt, in those areas where there's a particularly high concentration of chloride salts, you also, those may be the areas where preferentially you get these slope streaks to form over the course of the season.
And just one more, I'm trying to get an idea, if you have an idea of what the extent of that might be. Is there an ocean of that water, or a little bit, or a lot, or what, you know?
Well, if we're talking ice and we're considering the entire subsurface of Mars, there's probably at least a shallow sea's worth of water in ice form beneath the surface. But when we're talking about how much is available in liquid form, it's only these ephemeral, short-lived slope streaks that appear to be occurring over the course of a season.
Anyone have any follow-ups? All right, in that event, just a little bit of a programming note. We have 2 Mars briefings tomorrow. At 1 o'clock, we'll have a briefing on looking for signs of life in the universe. And then following at 2 o'clock will be our Mars Science Laboratory science briefing. So if you'll join us for those, 1 and 2 p.m. Eastern Time. And that will conclude this briefing. Thank you very much for coming. Thanks, George.
Well, NASA scientists are turning their curiosity toward Mars, literally. Curiosity is the name of the brand new space rover NASA is launching this Saturday. The unmanned vehicle costs $2.5 billion and is described as a dream machine by the space agency. The United States has launched 18 missions to the red planet so far. Now, the question remains, is there life on Mars? Well, let's ask CNN's John Zarrella, who joins us now live from the Kennedy Space Center. Is there?
Monita, let's see. If I had to guess, I'd say probably not anymore. There probably used to be. But, you know, I'm inside NASA's Vehicle Assembly Building, and, you know, this is the 4th largest building in the world by volume. And from here, they assembled the Saturn V moon rockets and the space shuttle vehicles. In fact, if we look over here, a little treat for the audience, there's the shuttle Endeavour being readied for its new home, the California Science Center, the museum out there that will take delivery of it in a year or so. You know, with the space shuttle program now over, NASA's turned its attention towards going to deep space. And tomorrow, not far from here, as you mentioned, they are going to be launching their largest rover ever to Mars. Mars. Does life exist there? Did it ever? NASA is poised to take its boldest step towards answering questions that could change forever our view of humanity's place in the universe.
I think the best way of saying why we're so excited about this mission is that it sets us up for the future of finally answering that you know, really age-old question of does life exist on other planets?
The mission is called the Mars Science Laboratory, or MSL. The most sophisticated vehicle ever sent to Mars, it has the capability to detect signs of life. If it works, come next August, after traveling 350 million miles, a 2,000-pound, 6-wheel rover called Curiosity will arrive at the red planet. Using a tether system never tried before, it will be lowered down to a place called the Gale Crater. The size of a small car, Curiosity is the Cadillac of rovers.
We're choosing to make the rovers bigger and bigger because we want to cover more ground. We want to be able to put an arm out and drill a rock.
Drill a rock? Why?
On Mars, if life exists as single-cell organisms, or if it ever existed, we believe it will be under the ground or inside rocks.
Inside Gale Crater sits what scientists believe is a layered mountain. In essence, the history of Mars told in the layers. And if water ever flowed on Mars, it might have been in that crater. Curiosity's arm will collect samples and place them in its onboard laboratory with the ability to detect organic material.
Now, if we discover organic materials on Mars, then it gets very exciting. You know, the chances of it may be low, but the payoff is huge. Organic materials are required for life as we know it.
But it won't mean life exists, just the building blocks.
If you go to the driest desert on Earth, can you find life on your samples if you do a year robotic study? Probably not. It's actually quite difficult. Life has to stick up and make itself seen.
Finding life itself would be left to the next wave of explorers, robotic and perhaps even human. Now for the engineering team out at the Jet Propulsion Laboratory in California that built Curiosity, this is a huge, huge deal because this is the last of the major planetary missions on NASA's book, so they are really hoping that this one is successful. Manita?
Yeah, fingers crossed there, John. Thank you so much. John Zarella there at the Kennedy Space Center.
Well, we continue to monitor developments in Egypt, where large Curiosity find life on Mars. Well, the brand new rover is set to launch on Saturday. It will be the biggest, most expensive and most sophisticated rover ever to hit the red planet. And John Zarella joins us from the Kennedy Space Center in Florida with all the details. Hello, John.
Hey, Annie, I'm inside NASA's Vehicle Assembly Building, which is the 4th largest building in the world. You can see the enormity of it, and the VAB is where the Apollo moon rockets were stacked and where the space shuttle orbiters were stacked to the external tank and the solid rocket booster. In fact, take a look over here, a little bit of a treat for the viewers. That's the Space Shuttle Endeavour. It's sitting here until the museum in California is ready to accept it. So, you know, with the Space Shuttle program now over, NASA is turning its attention to deep space exploration. And as you mentioned, they're getting ready, in fact, tomorrow morning, to launch the largest rover they've ever sent to Mars. Now, for the engineers out at the Jet Propulsion Laboratory in California who built Curiosity, hugely important mission because this is the last of the big planetary probes on NASA's books. And in fact, as we speak, the Atlas rocket that's going to be used to launch Curiosity is rolling out to the launch pad. Anna?
Fantastic. What access you get, John. Love your job. Now, just before you go, the Cadillac of rovers, how will it be powered?
You know, all the other ones have been powered by solar power, so subject to the climate on Mars, but this one is powered by what's called an RTG, radioisotope thermoelectric generator, so a nuclear-powered spacecraft going to Mars.
Sounds great. All right, John Zarella, great to see you. Thanks for that report.
Sure.
Well, a group of scientists is proposing new ways of rating an exoplanet's potential for hosting life. Well, one is the Earth Similarity Index. Rocky planets with water score high on it, but another index broadens the conventions we consider essential for life. Well, it's called the Planetary Habitability Index. On it, Saturn's moon Titan is considered to have the highest potential for life outside Earth. Well, Mars is a close second. Popular Science magazine spoke to one of the researchers behind this index, and he says Titan ranks higher because it has a thick atmosphere and lakes. But he also has this to say about Mars. There should be life on Mars. We just have to find it and confirm it. Now, one lady I know who loves space, and I would love to get her opinion as to whether there is life on Mars, is our own Mari Ramos. So, Mari, what do you think? Life on Mars?
Yeah, well, I need my space, definitely. So, yes, I love space. You know what? I think it's great that they're going out there to look for life because these things are going to have really, for lack of a better word, life-changing effects to our own life here on Earth. There are so many technologies that have been developed for space that now we use here on Earth. And see if Curiosity gets to launch tomorrow. There's about a 70% chance that the weather will cooperate. So that's pretty good, right? That the weather will cooperate at Cape Canaveral. So we're looking at the possibility of a few isolated thunderstorms nearby. They don't like to have any of that kind of stuff. And the winds, about 20, 25 kilometers per hour, are still within that threshold for having a launch. So that's definitely some good news there. Temperature's not a problem, into the mid-20s or low 20s by the time we get to that launch time at 10 a.m. local time. So pretty cool stuff there.
Neugier treibt die Menschen voran und Neugier bzw. Englisch Curiosity ist auch der Name dieses Erkundungsfahrzeugs, das demnächst auf unserem roten Nachbarplaneten, dem Mars, nach Leben suchen soll. Morgen will die NASA das hochmoderne Vehikel losschicken, um es dort 2 Jahre lang nach organischen Materialien suchen zu lassen. Zu diesen organischen Substanzen kommen wir später zurück. Jetzt zeigen wir Ihnen erstmal, wie es auf dem Mars aussieht, denn das weiß man schon ziemlich genau, obwohl ja noch nie ein Mensch seinen Fuß darauf gesetzt hat. Zu verdanken haben wir das einer hochauflösenden Kamera, die derzeit um den Mars kreist und die tolle 3D-Bilder sendet und die von einem deutschen Physiker entwickelt wurde.
Der Mars,
3D und in Farbe. Fast so, als wäre man vor Ort. Und das, obwohl der Planet zig Millionen Kilometer von der Erde entfernt ist. Wenn überhaupt, werden frühestens in 50 Jahren Menschen hier landen. Doch bis dahin werden wir schon unzählige Bilder vom Mars gesehen haben. Dank der Arbeiten dieses Forschers. Gerhard Neukum ist ein Pionier in der Kameraentwicklung für die Erforschung von Planeten.
Wir sagen immer scherzhaft, wir ziehen unsere Bäckerkleidung an, denn so ähnlich sieht es ja aus, aber es hat damit nichts zu tun.
Neukum hat schon in den 70er Jahren an den Apollo-Missionen mitgearbeitet. Wir folgen ihm auf dem Weg zu seinem Allerheiligsten, der hochauflösenden Spezialkamera HRSC. Ihre Zwillingsschwester kreist gerade um den Mars.
Das ist ein Exemplar, das identisch zu dem ist, das zurzeit gerade fliegt, um den Mars fliegt und Aufnahmen macht. Ja. Voll funktionsfähig, könnte eingesetzt werden auf einer Mission.
Seit den späten 80er Jahren arbeiten Neukum und sein Team an der Kamera. Die HRSC, ein absolutes Hightech-Gerät. Mit unverwüstlicher, ausgefeilter Technik zeichnet sie dreidimensionale Bilder von der Marsoberfläche auf.
Was ich hier in der Hand halte, das ist praktisch das Herzstück der Kamera. Das sind die lichtempfindlichen Sensoren, mit denen die Lichtsignale, die durch die Optik in die Kamera gelangen, aufgezeichnet werden. Also durch den mittleren Lichtweg fällt das Licht senkrecht auf den Sensor und bei den beiden seitlich angeordneten Fokalplatten fällt das Licht unter einem bestimmten Winkel auf die Fokalplatte.
Durch diese Anordnung der Sensoren ist die Kamera in der Lage, räumlich zu sehen. Mit dieser Technik waren Neukum und seine Mitarbeiter ihrer Zeit um einiges voraus.
Das ist für Weltraumeinsatz, Tiefraumeinsatz die erste Stereokamera, die jemals gebaut und geflogen worden ist. Ja.
Möglich wurde das europäische Prestige-Projekt durch eine Kooperation mit Russland. Nach jahrelangen Vorbereitungen schickt eine Rakete am 2. Juni 2003 von Baikonur aus die Mission Mars Express auf ihren Weg. 7 Monate später schwenkt die Sonde in den Mars-Orbit ein. Seitdem umkreist sie den roten Planeten und zeichnet permanent Daten von seiner Oberfläche auf. Diese sendet sie in regelmäßigen Abständen in Form von Zahlenreihen zur Erde. Dort angekommen, werden die Zahlen aufbereitet und in Bilder umgewandelt.
So, ne? Ja. Kann man sehr, sehr schön sehen, ja.
Die genaue inhaltliche Auswertung erfolgt am Institut für Geologische Wissenschaften der Freien Universität Berlin. Diesmal hat HRSC die Region des Mars-Südpols abgelichtet, in der Nähe von Ulysses Rupes. Die Interpretation der Bilder vom Mars ist Teamwork. Die Forscher sehen weite Eisfelder.
50 Meter pro Pixel.
Was ist das bloß für eine merkwürdige Geometrie hier?
Und mittendrin eine unerwartete Entdeckung. In einem Krater sichtet das Team einen riesigen Block. Die Vermessungen zeigen, der Krater ist rund 5 Kilometer breit. Der Block darin 1 Kilometer hoch. So etwas haben die Forscher bisher noch nie gesehen.
Noch jedes Mal, wenn wir neue Daten untersucht haben, waren Überraschungen da, haben wir etwas entdeckt. Ja? Mal was Kleineres, mal was Größeres. Ja?
In der Zwischenzeit treffen die Daten der einzelnen Farbkanäle ein. Damit können die Schwarz-Weiß-Bilder die typischen Marsfarben bekommen. Mit den Farben wird auch eine 3D-Ansicht möglich. Die 3D-Daten sorgen dafür, dass der seltsame Block besser untersucht werden kann.
Artefakte drin, aber die werden dann...
Die Forscher erkennen nun die Beschaffenheit.
Also da liegt dann drunter das DTM.
Ah, okay. Also wenn man sich das hier so ansieht, sieht das fast aus, als wäre das so in Wellen gekommen. Sieht so hier so unterschiedliche Niveaus.
Im Krater hat sich vermutlich ein Gemisch aus Eis, Geröll und Sand abgelagert. Mithilfe der Bilder der HRSC ist es den Wissenschaftlern so auch gelungen, Wasser auf der Marsoberfläche zu identifizieren. Schritt für Schritt gehen sie so der Frage nach, wie und vor allem, warum sich das Klima und damit die Atmosphäre des Planeten verändert hat.
Ja, und morgen fliegt nun, wie gesagt, ein hochmodernes Erkundungsfahrzeug zum Mars, um den Sand nach organischen Spuren abzusuchen. Curiosity wird dann Bodenproben nehmen, sie auf ihre Zusammensetzung untersuchen und ja vielleicht Spuren daran finden, die auf lebende Organismen zurückzuführen sind. Mal ein Beispiel. Bestimmte Kohlenwasserstoffe werden nur von einer ganz bestimmten Algenart produziert. Findet Curiosity diese Kohlenwasserstoffe im Sand, weiß man, dass es dort diese Algen gegeben haben muss und damit auch Wasser. Solche organischen Spuren werden Biomarker genannt. Wenn sie in Sedimenten eingeschlossen sind, können sie Jahrmillionen überdauern. Bei der Suche nach solchen Biomarkern auf dem Mars helfen nun die Erfahrungen, die Bremer Wissenschaftler in der Tiefsee gemacht haben.
Jetzt will es die NASA wissen. Bei ihrer Suche nach Lebensspuren auf dem Mars geht sie einen neuen, direkten Weg. Sie möchte Überreste mikrobiellen Lebens finden. Frühere Missionen haben gezeigt, Leben war theoretisch möglich, denn es gab Wasser. Nach was man suchen muss, wenn man Leben finden will, das kann man auf der Erde lernen. Auch in der Tiefsee wird heute noch intensiv nach Leben geforscht.
Wir gehen davon aus, dass sich das Leben im Untergrund des Ozeans bis zu mehreren Kilometer Tiefe erstreckt. Der Nachweis, der bisher erbracht worden ist, liegt bei ungefähr 1,7 Kilometer. Aber es gibt keinen Grund anzunehmen, dass es nicht noch tiefer gehen würde.
Kai-Uwe Hinrichs hat als Chemiker einen besonderen Blick auf die Entwicklung des Lebens. Seit 20 Jahren erforscht er die Lebensbedingungen an Orten, die auf den ersten Blick lebensfeindlich erscheinen. Ein wichtiges Archiv für seine Arbeiten ist das Bohrkernlager.
Hier befinden sich 140 Kilometer an Sedimentkernen, die überwiegend aus dem Atlantik und dem Mittelmeer stammen, und die decken insgesamt ca. 100 Millionen Jahre an Erdgeschichte ab.
Das Leben hinterlässt Spuren, biologische Moleküle oder kurz Biomarker. Und diese sind im Sediment eingeschlossen. Nach diesen Spuren suchen die Wissenschaftler. Auch Julius Lipp arbeitet in der Biomarkerforschung. Auch er ist Chemiker, der sich für die klassischen Berufsfelder nicht begeistern konnte und daher als erster Mitarbeiter bei Kai-Uwe Hinrichs anfing. Die Doktorarbeit ist inzwischen fertig. Mit der Biomarkerforschung in der Tiefsee ist er aber noch längst nicht am Ende. Er entwickelt Methoden, mit denen er dem Ozeanschlamm seine Geheimnisse entlockt.
Aus den Proben lösen wir Biomarker heraus, die wir später analysieren können, um Rückschlüsse zu ziehen, welche Arten von Organismen in den Sedimenten zu finden sind und auch wie viele. Und ich gucke mir im Speziellen eben die Biomarker an, die für lebendige Zellen stehen, und versuche eben herauszufinden, ganz einfache Fragen zu beantworten: Wie viele Zellen sind da, was für Zellen sind da und dann eben auch, was machen sie?
Für die Analytik benutzen die Wissenschaftler modernste Methoden, mit denen sie selbst geringste Spuren von biologischen Substanzen erkennen. Dann ist detektivischer Ehrgeiz gefragt. Denn nun müssen sie die Signale ausfiltern, welche eindeutig auf lebende Organismen zurückzuführen sind.
Wenn wir so eine typische Analyse machen, ist ein Großteil dieser Biomarker oft unbekannt, oder zunächst unbekannt. Das heißt, wir müssen in einem Puzzlespiel aus einzelnen Informationen uns eine Struktur zusammenbauen und dann diese Struktur auch noch in Beziehung zu einem Organismus setzen. Das ist oft eine Herausforderung, aber gleichzeitig ist es natürlich auch sehr spannend, weil wir in dem ja eben auch auf die Art und Weise erleben, wie wenig wir eigentlich über das Leben auf der Erde kennen.
Solche Untersuchungen werden nun auf dem Mars durchgeführt. Dafür soll ein mobiles Labor landen. Es wird von der Erde aus gesteuert und soll dahin fahren, wo die größte Chance besteht, mikrobielle Überreste zu finden. Dann wird in die Marsoberfläche gebohrt und es werden Proben genommen. Die Proben werden vollautomatisch gemessen. Biomarker wären der Beweis, dass es Leben auf dem Mars gab oder sogar noch gibt. Auf der Erde ist das Leben vermutlich an heißen Quellen im Meer entstanden. Auch hier suchen die Wissenschaftler nach Biomarkern, denn die Entstehung des Lebens auf der Erde ist immer noch nicht endgültig geklärt. Dabei ist die entscheidende Frage, wo das Leben eigentlich anfängt, gar nicht so leicht zu beantworten.
Wenn ich jetzt an Leben in den tiefen Sedimenten denke, dann bin ich schon überrascht, dass das Leben dort noch existiert. Letztendlich, weil wir oft Schwierigkeiten haben zu sagen, das ist die Energie, die die Organismen noch unterhalten kann. Also da ist auch momentan die Biologie einfach in so einem Grenzgebiet, wo man eben die Linie zwischen tot und lebendig gar nicht richtig ziehen kann.
Eines ist jedoch sicher: Das Leben findet auch unter schwierigsten Bedingungen einen Weg. Auf der Erde, aber vielleicht auch auf dem Mars. Die Biomarkerforschung macht sich jedenfalls auf den Weg in den Weltraum.
Mit ersten Ergebnissen vom Mars ist übrigens frühestens in 8 bis 9 Monaten zu rechnen. So lange braucht Curiosity, um den Mars zu erreichen. Ist die Landung sicher überstanden, wird es uns dann hoffentlich recht bald mit vielleicht spektakulären Neuigkeiten über außerirdisches Leben versorgen.
Hat es jemals Wasser auf dem roten Planeten gegeben? Genau das will die US-Raumfahrtbehörde NASA nun endlich herausfinden und setzt dabei auf Curiosity. Am Nachmittag soll in Cape Canaveral die neue unbemannte Mars-Mission starten. An Bord der Trägerrakete ist der Superroboter Curiosity, die größte und technisch raffinierteste Sonde, die bisher für die Landung auf einem Planeten entwickelt wurde. Das rollende Forschungslabor ist etwa so groß wie ein Kleinbus und wird voraussichtlich im August 2012 auf dem roten Planeten landen.
This thing can keep rolling for over 10 years. Now, I would think probably the devices, the mechanisms on the rover will wear out before its energy supply, its battery goes. But you know what? It's got a few years to have a look. It's gone to the deepest crater, or will go to the deepest crater on Mars. It looks from orbit as though the rocks in that crater were laid down when there was a lot of water on the surface. And we know that one of the things you need for life is liquid water. So certainly this location, 3 billion years ago, had that condition.
All of a sudden, I'm hearing Richard Burton's voice from the beginning of that album, War of the Worlds. Jonathan, you'll keep us company, I know, throughout the coming hours. In the meantime, thanks very much.
This is Atlas Launch Control. We are now just under 2.5 hours away from the launch of the Mars Science Laboratory and the Curiosity rover atop a United Launch Alliance Atlas V rocket from Launch Complex 41 at Cape Canaveral. The launch window today extends from 10:02 a.m. to 11:45 a.m., a duration of 1 hour and 43 minutes. The Curiosity rover will gather the soil and rock samples for the onboard laboratory equipment to attempt to detect chemical building blocks that will provide clues about life processes on Mars. With the liftoff today, the Mars Science Laboratory begins an 8.5-month journey to Mars, arriving in 2012 on August the 6th. The landing will occur at 3 p.m. local time at Gale Crater on Mars. At that point, the radio signals will take 13 minutes and 42 seconds to cover the 154 million mile distance between Mars and Earth. About 10 minutes ago, the launch pad was cleared of all personnel to begin preparations for loading cryogenic liquid hydrogen and liquid oxygen. Liquid oxygen will be loaded into the Atlas booster stage, the first stage, and will be followed by loading liquid oxygen and liquid hydrogen into the Centaur upper stage, or the second stage. We've just had a weather briefing by our launch weather officer, Clay Flynn, and we remain at a 70% go, 30% no-go as far as our launch weather criteria. At launch time, the temperature will be approximately 73 to 74 degrees. We'll have Easterly winds 18 to 21 knots, occasionally gusting to 24. Relative humidity of 70%, visibility of 7 to 10 miles. And we'll have scattered clouds for the most part. Occasionally there is a chance for a variable broken layer to appear. And as that occurs, should the ceilings become a launch constraint, then we will just simply wait that out as they pass over, which they're expected to do, and go into the next pane of the launch window, which occurs every 5 minutes. T-minus 2 hours in holding. This is Atlas Launch Control.
Atlas LO2 at 97.5%. Topping started.
Roger.
This is Atlas Launch Control at T-minus 35 minutes and counting. We'll be keeping track of the Atlas V's flight today through several different tracking stations around the world as the vehicle flies downrange and heads toward spacecraft separation over the Indian Ocean. The Air Force tracking station on the Kennedy Space Center, known as TEL-4, will track beginning at liftoff, and the Air Force Station in South Florida as well, near Jupiter Inlet, will pick up about 10 seconds after liftoff. They will be tracking the vehicle together until the Antigua tracking station acquires almost 6 minutes into the flight downrange. That will take us through all of the Bahamas and downrange islands, and as the vehicle moves into its flight over the Atlantic Ocean, the tracking and data relay satellite will pick up the rocket starting at about 12 minutes after launch. Once we reach Africa, the tracking station at Hartebeestok will begin covering. It will acquire about 32 minutes after launch. And once we get to the Indian Ocean, we'll have the tracking station at Diego Garcia at about 40 minutes into the flight, giving us confirmation of spacecraft separation. And also the tracking and data relay satellite system will be up as well through the Indian Ocean TDRS to support with communications to confirm that we've had separation and that's been a good clean spacecraft set. 6 minutes after spacecraft separation, then the Jet Propulsion Laboratory Deep Space Network station at Canberra in Australia will acquire the vehicle, and that will begin to give us some state of health information on how the Mars Science Laboratory is doing. We're hearing the various calls from the United Launch Alliance launch team, passing status to Scott Barney, the launch conductor for this flight. We're now at T-minus 32 minutes, 35 seconds and counting. This is Atlas Launch Control.
T-minus 32 minutes. T-minus 31 minutes. T-minus 30 minutes.
Start CISA, purge conditioning.
Roger.
Secure onboard video power.
Roger.
This is Atlas Launch Control, T-minus 29 minutes, 11 seconds and counting. We'll be getting a weather briefing by our Launch Weather Officer, Clay Flynn, in about 15 minutes. We can see on the satellite clouds coming in off the water in bands, and they will continue to pass through intermittently, and the criteria that we'll be watching for clouds and visibility to assure that we are go is one of the 13 criteria. This particular one says do not launch if the ceiling is less than 6,000 feet or the visibility is less than 4 nautical miles. So we should be good on the visibility constraint, but we'll be in and out perhaps on that ceiling less than 6,000 feet. And we're well in on the wind today, even though it may seem a little breezy outside. The Atlas can launch all the way up to 33 knots. At T-minus 28 minutes and counting, this is Atlas Launch Control.
Atlas LO2 fill and drain valve cycle test is complete.
Roger.
Atlas airborne vent valve functional test complete.
Roger. Perform POGO suppressor charge.
Roger.
T-minus 25 minutes.
Pogo suppressor charge complete.
Roger. And for a team, we're complete through step 4.151.
LC, step 4.159, FTS open loop test complete.
Roger.
T-minus.
This is Atlas Launch Control, T-minus 19 minutes, 50 seconds and counting. Coming up in the countdown, we have one remaining hold at T-minus 4 minutes. That will come at 9:48 this morning. That's a 10-minute built-in hold. We got a weather briefing coming up very shortly, in about another 7 or 8 minutes, from Clay Flynn, our launch weather officer, to tell us how things are looking for continuing on with the countdown. But we're all optimistic that this, at some time during the window, at the very least, we will be launching here today. The rocket, as we see it there on the pad, weighs 1,169,000 pounds. And when it takes off, it will be going with 2 million pounds of thrust as it clears the tower. And just the spacecraft, just the payload itself, weighs 8,463 pounds on top of the rocket. We're at T-minus 18 minutes, 23 seconds and counting. This is Atlas Launch Control.
Minutes. RD-180 transducer converter calibration complete.
Roger.
T-minus 17 minutes.
Fuel inlet valve is closed.
Roger.
T-minus 16 minutes.
Initiate fuel fill sequence.
Roger.
This is Atlas Launch Control at T-minus 15 minutes and counting. Right now we're making sure that all of the range support that are required for launch today are operating and meeting all of the criteria that we have. That includes not just our telemetry and radar coverage, which will be coming here from our Cape Canaveral and Kennedy Space Center Air Force facilities, but also downrange at the Air Force tracking station near Jupiter Inlet. And all of the optical, we have numerous optical sites around Cape Canaveral Air Force Station and on Kennedy Space Center and down at Patrick Air Force Base in Cocoa Beach, all of which collectively give us a required set of optical coverage that we must have to meet all of our range safety requirements. So they're looking at all of those right now to get a status on those to determine where we stand on having the necessary required optical coverage, as well as verifying all of our radar and telemetry links with the range. Once the vehicle lifts off today, it will be proceeding downrange on a launch azimuth of 97 degrees. And once we proceed into orbit, it will be on an inclination of 34.8 degrees. At T-minus 13 minutes, 35 seconds and counting, this is Atlas Launch Control.
T-minus 12 minutes. T-minus 11 minutes.
Target set. TS.
This is the LWO standing by for the L-20 weather brief on channels 3-8 weather brief and CC local in 1 minute.
This is Atlas Launch Control, T-minus 10 minutes, 33 seconds and counting. Standing by for our weather briefing from Launch Weather Officer Clay Flynn from the 45th Weather Squadron. And about less than 10 minutes after that, we'll have our NASA launch readiness poll from our launch director, Omar Baez. T-minus 10 minutes, 15 seconds and counting.
This is the LWO with the L-20 weather brief on channels 3-8 weather brief and CC local. Should have a satellite picture of the Central Florida Peninsula on your CCTV. You'll notice we continue to have clouds migrating at approximately 20 knots from east to west, heading towards about 290. At the present time, we are scattered at 5,000 feet. We may possibly go broken in between now and T0, but progging these clouds out, we should be scattered or forecasting scattered at 5,000 feet at T0. Taking a look at the radar, we do have some isolated showers out west of the pad that were coming in from the water, now west of the pad. Just a small threat of a light drop or two of rain through T0 or through the window. Taking a look at the winds out of Complex 41, present winds are gusting up to 19 knots. We did have peaks up to 26 knots as those light showers move through. We should expect to see gusts up to about 24 knots through the balance of the window. Winds from the east and expect them to stay from the east through the balance of the window. No change in temperature to speak of. Presently 76 degrees at this time, and we shouldn't have any significant change in that through the balance of the window. This is HR 1, 2, and 3. Pretty good agreement and not expecting a significant change. All LCCs are go at this time. In terms of the forecast, looking for scattered at T0. So at T0, scattered at 5,000 feet, and we'll continue to monitor should we not go at the beginning of the window or going into a broken condition. But expecting scattered conditions at 5,000 feet at T0, 7 miles visibility, winds from the east at 20, gusting to 25, isolated showers persisting, and temperature should be a little warmer than that, 75 to 76. 30% chance of violation, no change in the 24-hour. No change in the 48-hour, no threat of lightning, and proton flux remains at normal background levels and expected to remain so through the count. This concludes the weather brief pending your question, sir. I apologize, proton flux is slightly elevated, but well below the constraint, sir.
Thank you, Coordinator. No questions. Thank you.
T-minus 6 minutes.
Fuel fill sequence complete.
Roger.
T-minus 5 minutes.
Start lowest data acquisition.
Roger. Atlas LO2 at flight level.
Roger.
Centaur LO2 at flight level.
Roger.
Centaur LH2 at flight level.
Roger.
This is Atlas Launch Control, T-minus 4 minutes, 8 seconds, and counting, going into the hold in T-minus 5, 4, 3, 2, 1, T-minus 4 minutes, and holding for 10 minutes. Very shortly, we'll hear our NASA Launch Manager, NASA Launch Director, giving direction to continue with our countdown operations to come out of the hold after the hold expires in 10 minutes. We've had confirmation at this point that the Mars Science Laboratory spacecraft is go. And we'll be awaiting some final confirmation that all of the criteria we need to meet for the Air Force Houston range are go. We should get some kind of a status from Omar Baez, our NASA Launch Director, when he does his poll here in about a minute or so. At T-minus 4 minutes and holding, this is Atlas Launch Control.
Check channel 1.
Launch team, this is the NLM on the NLN net with our final launch poll and continuing the launch countdown at T-minus 4 minutes. NAM.
NAM's ready.
NASA CE.
NASA CE, go.
SMA.
SMA's go.
SMD.
SMD is go.
Mission Manager.
Mission Manager is go.
Copy that. The team's ready to release the hold at T-minus 4 minutes.
Red line monitor and event table are in the correct configuration for terminal count.
Roger.
LC RF. Go RF. Ready, Boris. Turn on the cameras.
Proceed.
Inward.
NSC, spacecraft to internal power.
Roger.
Perform launch on time verification.
Roger.
LC, switch to ready position.
Launch on time verified.
Roger. Status check to proceed with terminal count. Atlas systems. Propulsion.
Go.
Hydraulics.
Go.
Pneumatics.
Go.
LO2.
Go.
Water.
Go.
Centaur systems. Propulsion.
Go.
Pneumatics.
Go.
LO2.
Go.
LH2.
Go.
Hazgas.
Go.
Electrical systems. Airborne.
Go.
Ground.
Go.
Facility.
Go.
RFFTS.
Go.
Flight control.
Go.
Instrumentation.
Go.
COM.
Go.
GCQ.
Go.
Umbilicals.
Go.
ECS.
Go.
Redline monitor.
Go.
Quality.
Go.
OSM.
Go.
ULA safety officer.
Go.
Range, weather, and clear to proceed. Go.
LC, this is the LD on channel 1. LC, you have permission to launch.
Roger. Proceeding with the count.
NLM, this is SMD on NLM net.
Go ahead, SMD.
SMD would like to report that the spacecraft is on internal power and it's configured for launch for a T0 of 15:02:00.
Copy, SMD. MSL is configured for launch. While I have your attention, I want to wish the entire team that supported MSL good luck and Godspeed. It's been a long, challenging journey getting here, and we're proud to start you on the way to Mars shortly. NLM out.
Thank you very much, NLM. We really appreciate the thought.
1458 Zulu.
This is Atlas Launch Control, 90 seconds before coming out of this planned built-in hold at T-minus 4 minutes. Once we lift off, we'll be hearing our telemetry manager, Rob Gannon from United Launch Alliance, calling the flight events as the vehicle heads downrange. At T-minus 4 minutes and holding, with a minute and a quarter remaining in this planned built-in hold, this is Atlas Launch Control. This is Atlas Launch Control, 10 seconds remaining in this planned built-in hold, which will take us the last 4 minutes of the countdown, coming out in 2, 1, T-minus 4 minutes and counting.
355.
Ground power is enable.
Three minutes.
Securing Atlas stopping. Atlas tanks to flight pressure.
250.
FTS internal.
$159.
Vehicle power internal.
155.
Launch sequencer start.
150.
Securing Centaur LO2. Securing Centaur LH2.
140.
Launch enable.
FTS armed.
Cape Canaveral, Florida. Just moments from now, this rocket will blast off on a mission to Mars. All the details right here, right now, with the right stuff at the iDesk.
Live from CNN Center, you're at the International Desk with Jonathan Mann.
Cape Canaveral, and we're looking at an Atlas V rocket, one of the safest rockets, I have to say, a very, very good record. And on top, we have the largest, most capable rover that has ever been sent to the red planet. It weighs almost a ton, it carries 10 instruments, and it is going to look at the rocks on the surface of Mars to ascertain whether or not that planet has ever been capable of supporting life. So we're getting into the last few moments now. What will happen is that you will see the rocket underneath the launch pad. You'll see it ignite about 3 or 4 seconds before liftoff. They'll check the pressures, see that everything's fine, and then the strap-on boosters will be ignited, and at that point they won't be able to hold it, and we'll go. Let's listen into the commentary.
T-minus 15 seconds. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Main engine start, 0. And liftoff of the Atlas V with Curiosity, seeking clues to the planetary puzzle about life on Mars.
The program is in right on time. 180 operating at 100% plus as expected. And throttling down to 76%. Program is complete. And MSL is now breaking the sound barrier. SRB chamber pressures following the nominal curve. Everything looks
So there we go, Jonathan. And they do now, NASA, I've noticed over the past 3 or 4 years, they do now always, whoever does the countdown, just always does that little sort of romantic Hollywood thing, a little kind of mission brief, not aimed at scientists, but just telling us how glad they feel about it.
This is exciting stuff. You know, they've invested a huge amount of money. This mission, by the time it's completed, certainly its initial mission of 2 Earth years on the surface of Mars, will have cost NASA about $2.5 billion. So they've got every reason to be excited about it. We're seeing the Atlas flying out over the Atlantic at the moment. The first thing that you'll notice is that the solid boosters that are strapped to the side that give it that extra oomph, they will be split away once they've burnt. We're coming up on that moment now, and they'll come away in pairs. There are 4 of them on the main core stage, and then the Atlas will push on. It'll drop the lower half of the rocket, and then the upper half of the rocket will ignite its own engine, and it'll try and put the rover it's in a capsule at the moment in the top of that column. They'll put it into a parking orbit about 300 kilometers above the Earth. They'll wait a little bit, they'll just cruise on for a short amount of time, and then they'll ignite the engine once more and push on out towards Mars. We should get our first message, radio message, in about an hour from now. We'll get a signal from the cruise vehicle, this capsule that the rover is in. We'll get a message saying all systems are A-OK and we're on our way to Mars. And at that particular moment, they'll be moving at about 20 kilometers a second.
Wow. And then it takes 8 months to get there. It's there for 2 years. And it's big, it's chunky. Sadly, one remembers all those missions, not necessarily Mars rovers missions, where something very small, very flimsy goes wrong. But this one seems more robust in a way.
Well, we certainly hope so. A senior NASA official this week described Mars as the death planet. And the reason that she did that is because most of the missions that have gone to Mars have failed. I counted them up before I came on here. There was about 40, I think, since 1960 when the Soviets first went to Mars. 2/3 of those, Peter, have failed. It's extraordinary. 2/3 of the missions that we've sent to Mars have failed. It is very, very difficult to get down onto the surface in one piece. Now, they have a new rocket-powered descent system that they're going to try on this particular mission. It looks amazing. I have to say, as a commentator, there are an awful lot of events that must happen in sequence for that system to work. I hope it does, but a lot of people will be crossing their fingers in 8.5 months' time to see that it does get down.
And you were talking there about, the planning that's gone into this. One remembers when Barack Obama walked into the White House, because he had to, pulled the plug on an awful lot of what NASA was doing. So the feel-good factor about this, not just in Florida, where there's so much of tertiary employment off the back of what NASA does, but across the United States, the feel-good factor is pretty high as well.
Yeah, it's an important mission. One official described this mission as being as important to NASA as Hubble. And we know how important and how significant Hubble has been these last 20 years. But just to go to the manned spaceflight thing that you were talking about there, Peter, on this particular rover, this descent system that I was talking about, it is designed to put very large masses on the surface of Mars. Now, if we're ever to go there with humans, we're going to have to land more than a ton at a time. We're going to have to land several tons at a time. So this may well be the template for how we take humans to Mars in the future. And just to say, one of the instruments that's on this Mars rover is a radiation environment sensor as well, which is going to do the first sort of measurements that you would need in order to understand how safe it is for an astronaut to be on the surface of Mars. So yes, NASA has closed down a number of its options in the last year or so, but it's opening up new ones as well. And Mars is a very exciting destination.
And when it touches down, when it starts that process, you were telling me a little earlier, we won't see little creepy crawly things running across a microscope slide. But what's the thing that might hit the bullseye? What's the thing that the scientists will be looking at going, yep, there could be or there could have been life on Mars?
You need three things for life. You need liquid water. That's absolutely essential. Water is the thing that lubricates all of the biochemistry, if you like, in our bodies. You also need a source of energy. You and I know that plants need sunlight. We get our energy from eating food. And you also need a source of organics, of carbon-rich molecules, because we use that, microbes, bacteria, they use it to build and maintain their structures. Now, we've seen from orbit that Mars had water in the past. That's very clear. It would have had energy sources as well, but did it have a source of organics? Now, when we've looked in the past, we've never had absolute confirmation. This rover could give us that, and that would be a bullseye.
Jonathan, you'll keep us company, I know, throughout the course of the coming hours. In the meantime, thank you very much. Jonathan Amos, our science correspondent.
$120.
Orca's armed.
SCS count started.
Produce ECS for launch.
Roger.
110.
Vent valves locked.
T-minus 1 minute and counting.
Report range status.
Range status green.
That's step 3.
T-minus 30 seconds and counting.
28.
ECS reduced for launch.
25.
Roger. Status check.
Go Atlas. Go Centaur.
T-minus 15 seconds. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Main engine start, 0. And liftoff of the Atlas V with Curiosity, seeking clues to the planetary puzzle about life on Mars.
The program is in right on time. 180 operating at 100% thrust as expected. And throttling down to 76%. Program is complete. And MSL is now breaking the sound barrier. SRB chamber pressures following the nominal curve. Everything looking good. And we passed through max Q. We're on closed loop on Atlas PU. Signatures as expected. SRB profile continues to look nominal. Throttling back up to 100% thrust on the RD-180. Engine parameters looking good. Flight control disturbances look as expected. SRB pressures running right as expected. Coming up on SRB burnout, we have burnout of the SRBs. Everything is looking good. 10 seconds to SRB jet. And we have first pair and second pair. Both sets of SRBs have successfully jettisoned the vehicle. We've re-enabled guidance. Everything is looking good.
This is Rob Gannon, our United Launch Alliance telemetry manager. We're hearing.
Vehicle is now 32 nautical miles in altitude, 54 miles downrange, traveling at 4,900 miles per hour. And we've throttled down to hold a constant 2.5 G level for payload fairing jettison. And we fired the pyro valve, pressurizing the RCS bottle. Pressure increasing in the loop as expected. Now we're hitting our 2.5 G limit, coming up on payload fairing jettison, approximately 10 seconds. Fairing jet. And we also have a successful CFLR jettison, right as expected. Throttling up on the RD-180, everything looking good. Coming up to 89% thrust. And we are now entering our constant 4.6 G acceleration throttle phase. Everything looking good. We've started boost phase chill down. Housing temps are responding. Coming up on booster engine cutoff. Expecting BECO in 10 seconds. Safety ADUs. We have BECO, retro rockets, and stage separation. We have pre-start on fuel and locks. Ignition and full thrust. Center main engine is up and running as expected. Everything looking good. Steering has been enabled. We have center PU to fixed angles, right as expected. And we've begun our reaction control system thermal conditioning firings. Everything looking good. And the vehicle's now 102 nautical miles in altitude, 570 miles downrange, traveling at 13,700 miles per hour. And we're now in the early portions of a nearly 7-minute first burn of Centaur. Engine continues to operate normally on good steady state operating pressures. Engine continues to burn normally, seeing loop temps come up in the RCS system as we continue our thermal conditioning firings. Good AGCs on the FTS system. approaching RF disable.
This is the telemetry lab at NASA Hangar AE,
Atlas performance,
where all the data is coming in from the flight.
And we are rolling to TDRS.
Acquisition now through the Tracking and Data Relay Satellite System, TDRS East.
And we're continuing to roll to TDRS. Total of 75-degree change in attitude. Have switched to the Centaur-only format quite a few seconds ago. And we've achieved our TDRS attitude, roll rates coming back in. Engine continues to look good.
We've lost signal here at the Cape, as expected. Now using Antigua data.
And passing 470 seconds into the mission, everything looking good. And the vehicle's 150 miles in altitude, 1,250 miles downrange, traveling at 15,000 miles per hour. And we are seeing nice smooth responses from the flight control system. Body rates are smooth and very close to zero. We are accelerating at a steady 0.47 Gs. Engine continues to operate smoothly. And Centaur PU is in closed loop control, but continues to ride the stop as expected. And engine operating parameters continue to look good, nice and smooth.
Centaur engine cutoff coming up in 2 minutes.
We are 2 minutes to MECO 1. Vehicle's 151 miles in altitude, 1,648 miles downrange, traveling at 16,100 miles per hour. And taking a quick look at the range track, the vehicle is flying right down the projected path. Everything looking good there. We are now 1 minute to a nominal MECO 1. Expecting an IP vanish in approximately 40 seconds. And the engine continues to operate nominally. Centaur PU has come off the stop. It is actively controlling.
TDRS East is ready for the handoff from Antigua.
Pressures look good. RCS temps reacting as expected. Steadied out. Ten seconds to MECO 1. We have cutoff. Normal shutdown signatures. We have 4S engines on as expected.
Cutoff was right on time. Handing off
FTS
now
is
from
safe.
Antigua to Tidris East.
And we've begun our turn to MES 2 attitude. Starting to spin up Centaur in roll for our PTC roll. Taking a quick look, tank pressures are right as expected. Helium storage bottle pressures over 3,000 psi, looking good. Main battery voltage looks good. And we've achieved our 1.5 degree per second roll rate for our PTC roll.
This is Atlas Launch Control, 12 minutes 45 seconds into the flight. We had Centaur engine cutoff right on time at T plus 11 minutes and 30 seconds. And we are now in a parking orbit of 102 by 201 nautical miles. And we are underway with a 19-minute and 35-second coast phase, after which the Centaur will come up for a second and final time for an 8-minute burn to put it on planetary trajectory. We're going to show now some of the different camera angles of the launch of the Atlas V from different vantage points around Kennedy Space Center and Cape Canaveral Air Force Station. And we should have several different shots that will present different vantage points that will be particularly unusual from the standpoint of cameras that we have not used in the past. So we will begin right now with the launch replays.
We are continuing to see expected tank ullage pressure changes throughout coast phase. Battery voltages, storage bottle pressures, looking good. We are experiencing a data loss at this time. And we are seeing a little more data loss than expected. For coast phase, do have data back at this time, and everything looks good.
Right now our data is coming through the Tidris East satellite, and we'll be acquiring at Hartebeeststock once the vehicle is over South Africa at 32 minutes and 9 seconds into the mission.
Down to a 25% duty cycle. We have active data back here, and all levels look good for coast phase. And everything continues to look good for coast phase. And we're continuing to experience frequent data losses. When we do get some clean data back, all levels are as expected. And we've now got data back. Quick check, all levels look as expected. Another loss of data. And we've now steadied out at our 25% duty cycle on settling thrusters. And we received information the spacecraft is already power positive. We are continuing to see periodic data dropouts, though everything does look as expected when we do have acquisition of signal. And at this point in time in the mission, we should be seeing a PTC roll reversal, though we've not had data to confirm that. And we're approaching 1,300 seconds into the mission. Everything continues to look good. We are seeing expected levels in our bus battery voltages, as well as our storage bottles and propellant tanks. Body rates are looking good. And the next significant event we're looking for is a 2.5 second liquid oxygen flush through the propellant feed lines to condition the feed line for second burn. About 1 minute away from that. And we're approaching our duct flush milestone. However, a loss of telemetry is preventing me from verifying that activity. And we do have signal now. Taking a look at levels, everything is looking as expected. And we're just passing through 26 minutes into the mission. We are experiencing data loss at this time.
So this shows the second burnout of the Centaur, and the Centaur then orients us to be separated into the correct attitude for the cruise to Mars. And so we have power on the solar array, and we have good comm to Earth after we're separated. It takes about 8.5 months to get to Mars. We'll arrive on August 6th UTC, August 5th in Pasadena. About 10 minutes out, we throw away the cruise stage, and we enter the Martian atmosphere at about 12,000 miles an hour. You can see thrusters firing there. We use a guided entry on Mars Science Lab, which we did not use on Spirit or Opportunity. As a result, our landing footprint is much smaller, about 20 kilometers by 20 kilometers instead of about 85 kilometers by 15. That allows us to go to places like Gale Crater that we otherwise couldn't get to with the Spirit and Opportunity-like landing system. Then we throw away some mass to rebalance the spacecraft, and at Mach 2, about 1,000 miles an hour, we deployed the parachute. It's 23 meters diameter parachute. And when we go subsonic, we deploy the heat shield so that the radar can begin to get a look at the ground. When we're about a mile up, we deploy what we call the powered descent vehicle, which is the descent stage on top of the rover. And we fly the powered descent vehicle toward the ground. When we get a couple hundred feet up, we throttle down to, or throttle up to basically 3/4 of a meter per second constant descent. And we lower the rover on a bridle and deploy the mobility. And then where the bridle's about 13 meters long. And then we fly gently, I always say gently, to the ground and deposit the rover at about 3/4 of a meter per second vertical and about 2/10 of a meter per second horizontal. And when the descent stage senses that, it cuts the bridle and cuts the electrical cords, and the descent stage then flies away in a controlled manner, and we crash it about 3/4 of a kilometer away. The rover we won't raise the mast for the first day because we want to be sure that we've gotten a good stable platform. The rover weighs a metric ton, and if we're on some slope or on some rocks, we want to be careful in order before we begin to change the center of gravity. But on the second day, assuming everything is fine, we'll raise the mast and start to take photography and begin to characterize the rover, understand the vehicle integrity on the surface, make sure we understand its status, and then we begin to do first-time activities. Clearly, the simpler activities, starting the science instruments, simpler science instruments will be first. The more complex activities of driving will be second, and using the arm and sample acquisition will be third. This shows what might happen when we find a sample area that we would like to investigate further. That showed the chem shooting a laser at rocks. They vaporize the rocks, and we look at the plasma emission to determine the chemistry of the rock. And if we determine we have something that we would like and we want to sample, we would deploy the arm with its contact instruments and its drill. There are two instruments inside the rover that use samples from the surface, and the drill is a rotary percussion drill. My project scientist says, like you can buy at Home Depot, and actually augers dirt up into the drill where it is handed off to another piece of equipment which processes the dirt and dust and prepares it for putting it into the rover for the sample processing. So here you see the sample processing being completed and the sample being lowered, in this case, into the Chemin instrument. We also have a SAM instrument, Science Analysis at Mars. This one is an X-ray diffraction type of instrument, so the sample is put into a small cell, and we pass X-rays through it as we vibrate the sample to force the crystals to move and restructure themselves. And that gives us an X-ray diffraction pattern, which gives us crystallological information. We expect the rover to be able to traverse more than 20 kilometers in a 1 Martian year mission, which is 680.
5 seconds, spacecraft set. Achieved our targeted roll rate. We have spacecraft separation. And confirmation from our video system. And the vehicle has despun. And with the successful separation of the MSL spacecraft from AV-28, this concludes the commentary for this mission.
And we have lots of handshakes and smiling faces here in the control room because Mars Science Laboratory is on its way to Mars. This is Atlas Launch Control, 50 minutes 50 seconds into the flight of the Atlas V with Mars Science Laboratory and Curiosity. And we're standing by very shortly for spacecraft acquisition through the Canberra Deep Space Network tracking station. We have our NASA Launch Director Omar Baez here with us in the control room. And he's going to give us a brief indication of how the countdown went and how the flight looked to him. So, Omar, tell us how it looked.
George, the countdown went very smoothly. We worked a couple of minor issues, but none really on the launch vehicle or spacecraft, more dealing with communications and really fretting the weather or the clouds coming in, because it was one of the constraints for this one. And the count went very smoothly. We got off on the first opportunity at 10:02 in the morning, right on the money, and the flight looked great. Our parameters looked great, and we separated on time, and we had some spectacular video that I'm sure went out that confirmed that we did separate the spacecraft, and it looked to be in good shape. I know that they were power positive even before separating, so the MSL spacecraft has what it needs to survive in the next couple of hours, and we're just awaiting acquisition from the DSN now.
So spacecraft separation appeared to be clean from what we can tell?
From what I saw visually and on telemetry, that was a clean separation.
Well, we seem to have had a very successful flight of this Atlas V, and I think we have just had initial acquisition of the spacecraft through the Canberra tracking station. That's just been confirmed to us, so that's very good. So we've got it. And Omar, I guess we have another Atlas launch coming up sometime this summer, I think.
Yeah, the next Atlas up for us would be RBSP, or the Radiation Belt Solar Probe, and that will be our next Atlas V, currently scheduled for August 30th.
All right. Omar, thank you very much, and congratulations on having a very happy flight and a very happy spacecraft on the way to Mars.
Thank you, George.
We're now at 53 minutes, 23 seconds into the mission of the Mars Science Laboratory. This will conclude our launch coverage of this flight. This is Atlas Launch Control.
Curiosity rover on that rocket bound for the Red Planet. It is a self-contained science lab on wheels with a mission to search Mars for signs that the planet can support life or may have once in the past. CNN's John Zarella is at Cape Canaveral, Florida, where the rocket bearing Curiosity just blasted off. And John, if you're interested or intrigued by space, this is the most interesting question of all. Is there life out there?
Yeah, it really is. And, you know, the reality is, John, that this mission is not going to answer that question unless life kind of just sticks itself up and says, hey, I'm here. The reality is what they're going to hope to do, and they say it's still just a hope, is to find organic material. If you find organic material, that's a building block of life as we know it. You've got to have organic material to have life. And that would tell them that the conditions were present or are present for life to perhaps have existed or still exist on Mars. But the reality is, with this rover, it's so sophisticated that it'll actually be able to drill into rocks, take samples, analyze the samples right there on Mars in a mini laboratory that Curiosity carries with it, and give the scientists the answers to, you know, the chemical makeup, the chemistry of the rocks, what the minerals are, what they're made of. So it is a fascinating mission that is really, hopefully, going to get them one step closer to answering that critical question.
Okay, they're not quite hunting for Martians, but John Zarella is following it for us, and he'll keep us updated. Thanks very much.
Die amerikanische Raumfahrtbehörde NASA hat ihre neue Mars-Mission auf den Weg gebracht. Vom Weltraumbahnhof Cape Canaveral startete die Atlas-Rakete zu ihrer 9-monatigen Reise. Mit an Bord ein eigens für die Mission entwickelter Roboter. Nach rund 570 Millionen Kilometern soll Curiosity im nächsten August auf dem Mars landen. Eine seiner Aufgaben ist die Suche nach Wasser auf dem Planeten.
The Atlas V with Curiosity, seeking clues to the planetary puzzle about life on Mars.
Taking around 8 months to get to the red planet, and once it's there, it'll be there for 2 years. Jonathan Amos is our science correspondent. So far, so good. Just what's been going on in the past 60 minutes, Jonathan?
So this flight of the Atlas V rocket we see here from Cape Canaveral, that flight lasted about 44 minutes. They had to get the capsule. The rover is actually encapsulated to get to Mars. It's a vacuum in space, obviously, and it's very harsh. It can get very hot, very cold. So they put it inside a nice, comfortable capsule. Now, it had to be put into a parking orbit, they call it, first just above the Earth, about 300 kilometers, and then the rocket pushes on again, and it sends the capsule on its way to Mars. It'll need a couple of course corrections to finally get there in 8.5 months, but everything looks good. The capsule ejected from the rocket at just the right time. It's moving about 10 kilometers a second, so we've got our fingers crossed that everything's fine. They're talking to capsule at the moment, so we'll get full confirmation that everything is A-OK.
So once they get into that second stage, it then spends 8 months flying in a perfectly straight line for the planet.
Yeah, reasonably straight. They have to make a couple of corrections. The reason that they do that is because the rocket is following behind it, and they don't want the rocket also to fall onto Mars, because they don't want to contaminate Mars. There'll be microbes, Earth microbes, on the rocket. There'll be microbes, Earth microbes on the rover itself, and they want to reduce the amount of contamination that falls on Mars. So what they do is they just head off to one side a little bit, so the rocket misses Mars, and the capsule, they correct it, it lands on Mars. Hopefully. What you saw today was the easy bit.
You don't want to tick off any Martians with stuff falling on top of them.
No, but this was the easy bit today.
Right, okay. Once it gets there, what does it do?
It's got to get down. That's the first thing it's got to do. Most missions to Mars, most landing missions to Mars have failed. Something like 40 missions have been sent to the red planet since 1960, since the Soviets sent the first probe, and 2/3 of those have not got there. They've failed along the way, or they've crashed and burned. Now, the Americans have a reasonably good recent record, very good recent record. They've got some rovers down, 2 rovers recently, and a lander in the North Pole in just the last few years. So they have high confidence that this new rocket-powered descent system that they've developed can put the rover down on a button. It's going into a deep hole, a crater called Gale, and it'll touch down just to the right of it, and then it'll try and climb the mountain that's in the middle, which is 5 kilometers high.
Why not put it on top of the mountain?
Well, that's even more difficult. That's even more difficult. The base of the crater is flat, so you do what you can. You don't get ahead of yourself.
Okay, Jonathan, thanks very much.
Die NASA hat eine ehrgeizige Mars-Mission gestartet. Ein mobiles Labor soll die Oberfläche und die Atmosphäre unseres Nachbarplaneten erkunden. An Bord des Mars-Rovers sind auch Messgeräte, die von deutschen Wissenschaftlern entwickelt wurden. Heute begann die fast 9-monatige Reise zum Mars.
Der Mars ist nur etwa halb so groß wie die Erde. Aber er hat die gewaltigsten Canyons und den höchsten Gipfel im ganzen Sonnensystem. Er ist der einzige Planet, auf dem man Expeditionen unternehmen kann. Kurz nach 16 Uhr brachte eine Atlas V-Rakete heute das größte und raffinierteste Roboterfahrzeug aller Zeiten ins All. Das Ziel liegt in weiter Ferne. 354 Millionen Kilometer muss das Raumschiff zurücklegen, bis es im August 2012 ankommt. Mit an Bord sind ein paar Kilo Plutonium. Dieser Generator enthält 5 Kilo Plutoniumdioxid, das beim Zerfall Hitze abgibt. Diese Hitze wird hier in Elektrizität umgewandelt. Für die Landung hat sich die NASA ein neues Verfahren ausgedacht. Ein fliegender Kran soll das Landefahrzeug sanft auf der Oberfläche absetzen. Wenn alles gut geht, landet er mitten im Gale-Krater in der Nähe des Mars-Äquators. Dort ragt ein fast 5000 Meter hoher Berg aus dem flachen Becken. An seinen Hängen gibt es viele verschiedene Sedimentschichten. Daran wollen die Forscher die Klimageschichte des roten Planeten ablesen. Der Rover Curiosity ist so groß wie ein Van und wiegt 1 Tonne. Jedes seiner 6 Räder hat einen eigenen Elektromotor. Und mit seinem Laserspektrometer kann er sogar aus der Ferne die Chemie der Felsen untersuchen. Mit seinem Roboterarm gräbt Curiosity nach organischem Material, nach Spuren von Leben. 2 Jahre lang soll der Rover den Mars erkunden und mehr als 20 Kilometer zurücklegen. Als Vorhut für Astronauten, die eines Tages dort landen. Das wird wohl nicht vor 2030 sein.
Start der zweistufigen Atlas-Rakete, zumindest eher auf die Minute pünktlich. Denn die Mars-Mission der NASA beginnt mit 2-jähriger Verspätung und weit überzogenen Kosten, 2,5 Milliarden $. Dafür aber schwärmen die Ingenieure von einer Traummaschine. Der Mars-Rover Curiosity, übersetzt Neugierde, ist das bisher mit Abstand größte und leistungsstärkste Labor, das auf dem roten Planeten nach Spuren ehemaligen Lebens suchen soll. Im kommenden August soll Curiosity die 570 Millionen Kilometer Reise geschafft haben und den Landeanflug beginnen. Da sie mit 900 Kilo deutlich schwerer ist als ihre Vorgänger, scheiden die bisher verwendeten Airbags aus. Stattdessen soll der Himmelskran mit seinen Bremsraketen für eine weiche Landung im Marskrater Gale sorgen. Hier könnte es früher Wasser gegeben haben, Grundlage für Leben, vermuten Wissenschaftler. Gesteinsproben können mit Lasern verdampft oder mit einem Roboterarm in die Labors des Rovers gebracht werden. Hier warten unter anderem ein Hochleistungsofen, Röntgenspektrometer, ein Strahlendetektor. Die Erwartungen der NASA-Ingenieure sind gewaltig.
Ich von der NASA gestartet wurde, um den Mars wieder in einem Jahr, im August nächsten Jahres, zu erkunden, nach Spuren von organischem Leben, Voraussetzungen für Lebensentstehung,
das ist
nach Wasser.
Eine weltweite Freude.
Das ist das geht schon etwas über unseren kleinen, beschränkten Horizont der Erde. Ich muss Ihnen das erklären, Herr Lindner, ich habe immer so einen Spleen, wenn Leute sagen weltweit, ne? Dann sage ich immer, bleib doch bei der Erde, weil wir wissen über die Welt sehr wenig. Also es ist erdweit.
Er kann es nicht durchsetzen, aber hier am Tisch würden wir sagen, die Deutschen werden Erdmeister, nicht Weltmeister.
Ja. Es ist ein Anthropozentrismus dahinter. Nicht? Sie sind ja ein intelligenter Mensch, der im Grunde genommen wir sind der Mittelpunkt des Weltalls, was Galileo schon ad absurdum, selbstverständlich. Wir sind beieinander, ich sehe schon. Und deshalb sage ich immer, nutzen Sie das Wort Erdmeister, ne? Und Erdwirtschaft und erdweit. Also das ist die Freude, dass wir wieder was erfahren werden über den Mars.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Main engine start, 0. And liftoff of the Atlas V with Curiosity, seeking clues to the planetary puzzle about life on Mars.
Program is in right on time. 180 operating at 100% plus as expected. And throttling down to 76%.
Good afternoon, everyone. This is our post-launch news conference for Mars Science Laboratory and Curiosity, launched this morning on an Atlas V rocket. And here to talk about Curiosity and its state of health on the way to Mars and the agency's reaction to this launch is Pete Teisinger, the Mars Science Laboratory project manager from the Jet Propulsion Laboratory, John Grotzinger, the MSL project scientist from the California Institute of Technology, and Doug McQuestion, the director of the Mars Exploration Program at NASA headquarters. And we'll start first with the MSL project manager, Pete Teisinger. Pete.
Good afternoon. Our spacecraft is in excellent health, and it's on its way to Mars. Okay? And questions? I'm sorry. I'll talk about spacecraft health in a second, but I want to give a tremendous thanks to the launch team, ULA, and to the Launch Service Provider Organization here at Kennedy, and to Kennedy Space Center, who's been have hosted us since we arrived in May and June, and built up the spacecraft and did final testing here and finally encapsulated for flight. They did a tremendous job today. They've done a tremendous job for all these months, and it was a fantastic and smooth operation today, really just first-rate and tremendously professional. As I said, the spacecraft is in excellent health. You may have seen pictures of the separation. Weren't those fantastic photographs? And we separated perfectly on time, of course, and the acquisition of signal was as expected about 6 minutes later, 15:52:27. If you want to know, Zulu. The power, we are power positive, slowly charging the batteries. We did not lose that much state of charge, in fact, during the ascent profile. We're thermally as expected. The cat bed heaters for propulsion are on. The temperatures are as we expect them on the key pieces of equipment, and we're changing slowly, as you'd expect, as we transition from ground-based to space operations. We are in cruise mode. We have commanded the spacecraft, and we are therefore in two-way and are getting navigation data. The injection was first rate, much less than 1/10 of a sigma is both ULA and our navigation estimate. So it was a fantastic, accurate injection. And that's about it for me. Very happy guy.
Thank you, Pete. And now John Grossinger, the project scientist from the California Institute of Technology. John.
Well, I'm also really excited, I think, on behalf of every scientist on this mission, and there are about 250 of us. I would like to thank every engineer at JPL, everybody that has worked so hard for almost 10 years to build this spacecraft, put it together, all the principal investigators who have dedicated their lives to building the instruments for just as much time, and all their team members that have helped with getting surface operations. We are ready to go for landing on the surface of Mars, and we couldn't be happier. I think this mission will be a great one. It is an important next step in NASA's overall goal to address the issue of life in the universe. We are not a life detection mission. We have no ability to detect life present on the surface of Mars. And it is important to distinguish that as an intermediate mission between MER, which was the search for water, and future missions, which may undertake life detection. Our mission is about looking for ancient habitable environments and a time in the history of Mars that is very different from the conditions that you see today on the surface of Mars. We have a lot of evidence that has brought us to a single landing site, the result of 6 years of deliberation over more than 50 potential landing sites. The engineering system on this mission that will land us on the surface of Mars for the first time in the history of any landed mission to Mars gets the scientists to exactly where they wanted to go. There's no compromise. We are going to the very best place that we could find to go to, and I just can't wait to get on the ground.
Thanks, John. Now, Doug McQuestion, the director for NASA's Mars Exploration Program at NASA headquarters. Doug.
Ecstatic is the word. I mean, the agency has been working this mission hard with JPL and all the other organizations such as Department of Energy, our international partners, and now KSC and ULA have put us right where we wanted to be. Moving fast, cruising to Mars, hot, straight, and normal, right? In good shape. So the agency is ecstatic. I mean, we have started a new era of exploration of Mars with this mission, not just technologically, but scientifically, as John said. I hope we have more work than the scientists can actually handle. Once we get to the surface, I expect them all to be overrun with data that they've never seen before. I expect the public to have images, vistas that we've never seen before either. Down in the bottom of Gale Crater when we land, those first images are going to just be stunning, I believe. It'll be like sitting at the bottom of the Grand Canyon, I think. So we are absolutely ecstatic. Can't wait to get to Mars. Also need to thank the JPL team. Pete, you and your guys, John, for getting us to this point. It's an enormous mission. It's equivalent of 3 missions, frankly, and quite an undertaking. Science fiction is now science fact. We're flying to Mars. We get it on the ground and see what we find.
Thank you, Doug. We're ready now to take questions. Please give your name and your affiliation when the microphone comes to you. Let's start here in the front with Marcia.
Marcia Dunn, Associated Press, probably for Mr. Theisinger. But, you know, we've heard that the Bermuda Triangle awaits you. How, is that even on your mind today? I mean, are you quickly putting the launch behind as a success and now looking forward to this 8-month cruise, or?
What launch?
What launch? Yeah, exactly.
Well, you can't, you know, we clearly been thinking about intercent landing for quite a while, as well as thinking about the surface mission for a while. But you gotta, you know, today's today, and we need to let everybody enjoy the moment. We all recognize this is the prologue for the mission. necessary, but not sufficient. And we all have our work cut out for us in the next 8.5 months to prepare for a surface mission and do the final I-totting and T-crossing for EDL. But today's a great day.
Right here.
Jim Siegel, Celebration Independent Newspaper. I believe this one might be for Doug. I noticed in some of the press materials that we received, there have been maybe 20 or 30 different missions that have been sent to Mars, or at least attempted, since 1960. And there are several that are planned, or perhaps not budgeted, but at least planned. And I wondered if you could tell us a little bit about what the next step is after Curiosity and the Mars Science Laboratory.
Sure. The next mission is an orbiter, the MAVEN mission. So we'll be back in 26 months. So we told the ULA guys and the Kennedy Space Center folks this morning to be prepared. We are coming back. So MAVEN mission is an exciting mission. It is an orbiter, as I mentioned, but it's also an atmospheric escape rate mission. So one of the keys to what's happened to Mars and moving it from I'm talking about your category now here, poke me when I say it wrong, moving from a wet planet, a warm and wet planet in the past, to a cold, dry planet that we know now with water that's significantly under the surface but at the poles, is what happened to the atmosphere. And MAVEN's mission is called Aeronomy, and the job is to try to help understand what the escape rates of the atmosphere are now, the interaction with the solar wind, and if we can try to understand the history of the atmosphere that actually helped change the planet. So it's a planetary evolution, in a way, mission. That's the next exciting mission. That's a 2013 launch. And after that, we're still in discussions with the Europeans. We're looking at, as you said, there's a number of different missions that we're planning, potentially trace gas missions, which is what we'd like to do. Hopefully another lander in 2018 that will continue moving the science forward, that MSL will start in that new era of seeking the signs of life.
Just a quick follow-up. How many additional missions would you envision then between now and when we might actually try manned exploration of the planet?
There's a series of precursor measurements that need to be done, better understanding of the dust and of the regolith and how it interacts with hardware and equipment, toxicity of the soils, how easy it is to extract water and things from the materials that we have on the surface, and maybe other materials that could be useful. That's a series of precursor missions that we actually don't have on the books quite yet. We've had years of discussion about what those might be and how to go about those things. But there's a balance of scientific missions and human exploration precursor missions that have yet to be discerned, what that balance is going to be. The big issue with getting humans to Mars, frankly, is entry, descent, and landing. Pete and the team, the Mars Exploration Program, are about to put the largest vehicle on the surface ever put down, a metric ton, well, 900 kilograms to be exact. When you're talking about humans to Mars, you're talking an order of magnitude almost more than that. You're talking, well, a couple of orders of magnitude in some cases. You're talking 40, 50, 60 kilotons and metric tons, excuse me. We don't know how to do that yet. We actually don't know how to do that yet. That's more of the technology tall pole than the scientific precursor missions are.
Thank you.
Mm-hmm.
Irene?
Thanks. Irene Klotz with Reuters. In one of the earlier briefings this week, I guess it's still, Mike Malin was talking about the huge amounts of data that will need to be coming back just from the images. And I was wondering if any of you could just talk a little bit about what your plan is for managing the communications and if there's a backup in case MRO, something happens with it and that's not available.
You want to talk, Alan?
They seem both to be looking at me, don't they? Well, we have UHF relay communications planned through both Odyssey and MRO, and we do have a very, very limited X-band communication with the ground. So I think that we will prioritize the data and send it down in the priorities that both the engineers and the scientists want to have. It is likely that with the cameras being able to take so many pictures that we are going to have data that we're not going to be able to ever return. I think that we will have to prioritize and send it back, and that's just the fact that our telemetry link is not as good as our data acquisition process on the planet. I think that We firmly expect MRO. There's no reason not to believe that MRO will be there for the entire mission and do an extended mission. I think Odyssey is a little bit more of a question mark, although the latest data I've had on its gas utilization indicate that it is still quite an expected life. So that's where we are.
If I can inject on that also, Maven is carrying Electra radios also. So Electra radios are a software reprogrammable radio that it does the primary uplink, downlink from the surface. And so as we go through orbiters, that's why this program is set up as a program, and it's not just individual random missions. That's one of the reasons. So we will refresh that telecom capability of Odyssey and MRO when Maven flies, because it'll take an Electra radio to the planet as well.
I also had a science question maybe for you, John. I was just kind of curious if this suite of instruments that are on Curiosity was on the Viking landers, do you think that the results would be any different? Or do you think that the place where the Vikings landers touched down is just completely kind of antithesis to any search for organics?
Yeah. I think if you had the Viking Lander 1 and Viking Lander 2 sites on the list today, they wouldn't have made it past the first landing site workshop. And you sort of in those days you get what you can get to and hope to make the most out of it. The big difference we've got now is with the rover's capability is that we are A, mobile, and B, with all the instrumentation and all the people working on the mission, we have a much better chance to focus in on areas that we think are promising for the goals of investigating past habitability.
Okay, Craig.
Thanks. Craig Cavalt with Aerospace America. Kind of a lessons learned to this point question on development. I think you'd agree that the development of MSL was perhaps a bigger task than NASA believed it would be at the start. If you had it to do over again, what would you do differently?
You want me to take that one?
Yes, I do.
I thought you would. NASA's here to do the hard stuff. If we were doing the easy stuff, we wouldn't be NASA, I don't believe. Have we learned lessons? Yeah, we sure have. We've learned lessons about how to manage certain things. We've learned lessons technically, what works, what doesn't work. We've learned lessons about lead times. We really needed those 2 years that we took. And it was important that we did that. It was money that we're going to see real shortly is well invested. But whenever you're pushing the envelope, scientifically or technically, it's going to be harder than you think it is. So I think the length of time we have for development is one of the key lessons that we've learned. And our intent as we go forward is to make sure that we aren't compressing the different phases of design and development when we're actually trying to do something new and challenging.
Yes, right back here.
Hi, Robert Perlman with CollectSpace.com. Sort of working off of Irene's question earlier about communication management, how will Curiosity's arrival on the planet affect Opportunity's mission? Will priority be given to Curiosity in terms of communicating with Earth?
I don't necessarily think that's an issue. We have the two orbiters. We are able to track both orbiters at once with multiple aperture per multiple spacecraft for reactor capability for DSN. So right now I don't see a tremendous conflict in terms of our data needs and Opportunity's data needs as we go forward. Certainly hope that Opportunity is there, so we have that opportunity to share the link with that.
Okay, hi, Mike Wall from Space.com. So you guys are going to be gathering a ton of data, and there's going to be a real bottleneck in terms of sending it home. Can you just kind of talk about what that's going to mean for folks who are not necessarily scientists but are interested in what you guys are discovering, like the views and the videos? How fast are you going to be able to get that stuff down? And I mean, how much are we kind of going to be able to see of these vistas that Curiosity is seeing?
I think John may correct me, but I think our current data rate is around 250 megabytes per day that we should get down. So that allows quite a rich amount of data. I don't in my caution before, I certainly didn't want to indicate that we're going to get 1/10 or 1/100th of the pictures down. I don't think that's the case. but certainly we're not going to get 100% of the pictures down. And we will pick and choose because the scientists will want very much to get the right context pictures to do the rest of the science investigation that they need to do.
Let me just add to that a little bit. The principal investigator, Mike Malin, when he designed the cameras, each camera has its own buffer, which is 8 gigs. And the science plan this time around is going to be a little bit different than what happened with MER. On MER, the science team would look at the NavCam images and then based on those, select some subset of images to then shoot with the PanCam. This time around, what the PI would like to do is shoot a broader vista right away and return thumbnails. All thumbnails will come back. Then the science team will actually look at those color thumbnails and from that be able to select what subset you would actually downlink. So the buffers exist as a data management process to allow much bigger data sets to be acquired with the full intention that some subset of it will never be returned probably.
Scott Powers from the Orlando Sentinel. Pete, are there any upcoming significant milestones or challenges between now and August for this flight, or is it just going to be an ice cruise for 8.5 months?
Yes, we've got an engineering checkout that will occur in a few weeks and a science instrument checkout that will occur sometime thereafter. We have, of course, 6 trajectory correction maneuvers to engage in. The first one will be about 15 days out from today. The second one approximately 2 months out, and the third one about a month or so before we get to Mars. And the last 3 are for fine-tuning the entry, descent, and landing corridor. We are also planning 2 software loads. One in May to be the final update of the software for EDL and in the last phase of the mission, and one in June for a surface mission. So those are the key kind of major events that will be engaged on the spacecraft. On the ground, we'll be engaging in operational readiness tests, and we have about 10 planned between now and August. So we're going to be clipping off at more than 1 a month, 3 of them for entry, descent, and landing, and 7 of them for the surface operations.
To clarify, you said there are 3 trajectory changes between now and when it reaches Mars?
Right. There's a major aim bias that takes place when you go to Mars because the second stage, the Centaur is also going to Mars. And it's not treated from a planetary protection standpoint the same way the spacecraft is treated. So the aim point right now is quite a bit away from Mars. And so the first trajectory correction maneuver will be to correct the aim point for what we want the entry point to be. All the trajectory correction maneuvers after that are basically to take out the errors of that first trajectory correction maneuver.
Okay, Ken?
Hi, Ken Kramer for Spaceflight Magazine. Question for John. You said the other day and today also this is not a life detection mission. I wonder if you could describe a little bit what kind of instruments you'd like to have to make it a life detection mission in the future. And a question for Pete. When you do get to Mars, you're going to be monitoring the weather so you can make last-minute changes in the entry, descent, and landing profile at all? And other atmospheric data, too. Thanks.
You're up first.
All right. So what I would want is lots and lots and lots and lots and lots and lots of rovers, because what we learn on Earth is that you need lots of humans to go out in the field and rocks that are 3.5 billion years old to actually find something that you can look at and hold up and hold a press conference like this and say, I found evidence of life on the early Earth. And again, I'll emphasize this throughout the mission. The great paradox here is that water, the very thing that enables life, when you convert loose sediment that might have microorganisms in it, and you convert that to solid rock, that requires circulation of many, many pore volumes of water, and water is an oxidant. So the water actually oxidizes the organics. And on Earth, the exploration for fossils that might be present in ancient rocks is quite serendipitous. You have to sort of learn how to get to a good spot that looks promising in terms of kind of cementing the material in very early on. If it happens later on, that's no good. You want to get it early on because most microorganisms degrade within hours or days. So you got to get them locked in early. And with that paradigm, then you begin to just poke around, and it's just really just collecting many different kinds of rocks. So I would imagine that what we could do as far as exploring ancient Mars is concerned is you do need to explore probably a couple of different of these landing sites and learn to become familiar with the patterns by which water converted materials, including potential organics, into rocks. So, and then in addition to that, you would need very specialized microscopes that you could use to take rocks on Earth. We cut them so thin you can pass light through them, and then you can see actually cellular structure and distinguish that from abiotic processes. The other option is to find what you think really is sort of the glory hole and get a piece of it and return it back to Earth. So, you know, I think that latter option is the direction that the Mars program is headed in.
Okay.
The current instruments on MRO and Odyssey and Mars Express will in fact look at the atmosphere and give us data on any changes in the atmosphere that we might see. We don't expect this to have a dust storm because this is not dust storm season, but there could be inflation in the atmosphere as a result of other processes. Our entry, descent, and landing simulations and testing has taken a look at extremely broad atmospheric distributions in terms of pressure and density profiles. So I don't expect any surprises there, but we will of course fine-tune the entry, descent, and landing timeline based upon what we see.
Gene McCulka with Talking Space. Question for John. We got a good idea of what the engineering side is doing on the cruise out. What is the science side going to be doing on the cruise out?
Right. So Pete mentioned operational readiness tests, and we have several of those planned for the science team. And what we do is we work with Curiosity's twin, which is back at JPL in the test bed there. And it has a high degree of fidelity compared to what the spacecraft is. It's on its way to Mars. And with that then, we undergo tests where the team actually thinks about what kind of sequences they would like to acquire on the surface of Mars, as it were. They get implemented, they get built, they get radiated to Mars, the data gets returned back to Earth. And in the simulation, then the science team gets to practice with, for example, how you would do triage between the amount of data that's available, the amount of power that's available, the amount of time that's available. Basically, the three fundamental resources that allow us to do the science experiments. And so then, you know, we hope then with the 10 instruments to be able to learn how to efficiently do trade-offs and work with the flight software and interact with the engineers that will be required to help us do everything, and lots of training there. Yeah.
I'm Roland Keller of Swiss Engineering. After this beautiful flight, I would like to know what do you think about the international cooperation after the program ExoMars?
I think I have to answer that one. You know, we've been working with the European Space Agency for several years now, and you know, we are continuing to do that. We met last night to continue discussions. It's a very important partnership for us, NASA, with both the 16 mission and the 2018 mission. We continue to pursue those, and my 2012 budget that was just passed by Congress recently supports that activity, and we will continue pressing that. As you know, we have excellent international participation on MSL. I hope I get them all. Canada, Russia, France, Germany are all aboard. And Spain, thank you. And Spain are all aboard. I knew I'd miss one. It's been a long day. And so, you know, we work with the international community all the time. And this is expanding that with ExoMars, and we intend to continue to pursue that. So we want that to happen.
Todd?
Todd Halverson of Florida Today. I was wondering if you could tell us what you anticipate to get out of the descent camera, what we will actually see as a product of that instrument, and when we might see it.
So the descent camera turns on just moments before separation of the heat shield, and it acquires all the way to the surface at about 5 frames per second, full color HD resolution. And then after we touch down, it shuts off nominally. That camera is available to use throughout the mission on a best efforts basis after that. So that data set will be a very large one, and given the fact that we will want other critical engineering data to come down and also some other initial science products to come down, our guess is that probably initially within a week or two, there will be a subset of the frames that will be a pretty nice looking movie that will be available, and probably within a few months it will be required to downlink all of the frames that would give you the complete sequence, something like that.
Any further questions? Yes, we have one over here.
Thank you. Jackie Goddard for the Sunday Telegraph of London. Already our launch coverage online is generating the usual array of reader comments that say, that question the amount of spending on a mission like this, and why aren't we feeding the world starving and frivolous and waste of money. Do you find that kind of attitude demoralizing, and how do you redress that lack of understanding of the importance of this science that you're doing?
Yeah, I think any one of us could take that, but Pete and I have often discussed this, especially in the context of the 2-year slip. You ask in retrospect, what does it mean that we've done that? I think you look back, and at least for this country, you take every child, woman, and man, and you divide the total price tag by the number of people, and it comes out to about the cost of a movie. So, I'll leave you to judge for yourself whether or not that's a movie you'd like to see. I know that's one I would. I think the cost is a bargain for education for all the science team members that represent other countries as well. This is the stuff that fuels kids' imaginations to go into science and engineering. I can't think of anything better. I have a lot of friends of mine whose kids were watching early this morning at JPL, and it's about as good as it gets, and I think that's a great investment.
I'd like to add the standard cliche to that, however, which is we don't spend any money on Mars, right? We spend it all here. These are high-tech, good-paying jobs across the country that are created when you do something like this. I've not actually counted it up, and I know that there are thousands of individuals across the country, anywhere from high school educations to PhDs, that are gainfully employed, exciting other people, as you said, to bring more kids into the engineering and sciences. And frankly, that's what moves society forward. Very important.
All right, if there are no other questions, we're going to conclude, but as we go out, we're going to show some video of the spacecraft separation today, which everyone agrees was quite mind-blowing. So we're going to go ahead and we'll show that, and then that will conclude this briefing. Thank you very much.
Seconds, spacecraft set. Achieved our targeted roll rate. We have spacecraft separation. And confirmation from our video system. And the vehicle has despun.